Hello guys, good morning. How are you all? Am I audible? Am I visible? Okay, let me just check. So on the last class we talked about so in the last class we discussed about the dimension analysis. So let's take a couple of classes, then we'll go for assignments. Okay. And during the lectures also we'll be considering some problems. Let me share the link. So in this lecture basically we'll be uploading the lectures, or we'll be taking the lectures in English, explicitly in English. So just a moment guys. So if you did not subscribe the channel, please subscribe it, and we'll try to cover mathematical methods and few other subjects in this channel. Okay. Okay, so now without any further ado, okay, let's start. Now this is one of the very important topic and very easy topic also, will not take much time to cover. So briefly there are a few things. Initially you have to get some idea about some vector identities, then we'll go for some vector related theorems, and mainly problems will come from the vector related theorems. Then we have line integral, surface integral, volume integral. So from these topics questions are highly probable. And guys, if you have not downloaded our Physics Hub application, you can download it from Play Store by searching this Physics Hub, or you can just scan this QR code and you will get this app. Let's talk about vectors. What is vector? What is a vector? When do you call it something a vector? So there are two types of physical quantities: scalar quantities and vector quantities. And the quantities which have only magnitude but doesn't have any direction, those are called scalars, and the quantities which have magnitude as well as direction. Okay, so let's start with the definition for the sake of completeness. So physical quantities which has both magnitude and a finite direction are called vectors. So this is the first thing, but being a senior student, you should remember that vectors should follow the vectors law of addition. Okay, this must be followed, then only it will satisfy to be called as vector. The controversial quantity, you see, current has magnitude, but it also has direction, but current is not termed as a vector quantity because it doesn't follow the vector law of addition. So this is very primary thing, and let me show you this one. Look at this one. In this figure you are seeing this. So length of this line basically gives you the magnitude, and direction is direction. So if I am drawing two vectors, let's say this is one vector and I am taking another vector in the same direction. So what is the difference between these two vectors? So although they have same direction, let's say n-cap direction, both of them have n-cap direction, but the magnitude of this vector is larger than this. So sometimes by the length the magnitude is noted. So this is the basic idea of vectors. Now many primary definitions are there of vectors. We are not going into that. We are directly going into the orthogonal resolution of vectors. How we get the orthogonal resolution of vectors, that is important to know because that is very fundamental, and from that we will extend our discussion later on to different coordinate system. So initially we will stick to the Cartesian coordinate system. So you can give the heading orthogonal resolution of vectors. So we are considering a vector in a three-dimensional Euclidean space. So as usual, normal three-dimensional orthogonal coordinate system. So three axes are drawn in this way: x, y, and z. We are taking this course as if you are starting from very beginning. Okay. So that is why we are covering this simple thing also, although you already know, but keeping in mind that your basic is not so much clear, we are covering this. So this is equally helpful to advanced level students and the beginners also. Mainly we are targeting for the beginners. So this is x-axis, this is y-axis, and this is z-axis. Now how do you draw a vector? Let's say this is the origin. Now we have a vector. We get the vector by joining a line like this. So let's say OP is the vector. So how the resolution will work? Orthogonal resolution means, you see, its component along x-axis, y-axis, and z-axis, and you see x, y, and z, they all are perpendicular to each other. That is why the meaning orthogonal resolution of vectors. So let's say we are calling this vector to be A. Okay. So any vector A in the 3D right-handed, okay, 3D right-handed rectangular Cartesian coordinate system can be represented as so this vector, you see how we denote OP, initial point, final point. So the OP is a vector which we call vector A. So this will be, you see, if you look at this, how many components it has. If you want to reach to this point P, what you have to do, you have to first go along x-axis, then you have to go along y-axis like this, then you have to go along z-axis. So this much, the amount you go along x-axis is ax, the amount you go along y-axis is ay, and the amount you go along z-axis is az. Then you finally reach to this point P. You started from O reaching to P via ax, ay, az. So these are the components along x-axis, along y-axis, along z-axis. So we write it in this way: ax I cap, ay j cap plus az k cap, right? Here I, j, k are the unit vectors along x-axis, along y-axis, and along z-axis. I cap, j cap, k cap. So these vectors are also expressed sometimes as x cap, y cap, and z cap. So these are same thing, okay? Either you write x cap or I cap, j cap or y cap, or z cap or k cap. So they are same thing. And what are these x, ax, ay, and az? These are the rectangular components. Rectangular components of vector A along x, y, and z axis, right? And how do you write the magnitude? You write the magnitude of vector A look, this is very fundamental thing. Once you go to the other coordinate system, the process will be same, the quantities will be different. Just we write it as A mod. So this is equals to root over ax square, whatever be the components, x component square, then ay square, az square root. So this one you need to remember. For complicated expression also, we will be using the same formula to calculate this magnitude of the vector. Now if I want to calculate the unit vector along the direction A, okay, so unit vector along the direction of A is written as a cap. The basic definition, this is vector symbol, this is a unit vector direction. So unit vector along A is written as a cap, and a cap is defined in this way: vector A divided by modulus of vector A. So vector A, we have already got it, ax I cap, ay j cap, az k cap, divided by the magnitude. What is the magnitude? Is root over ax square plus ay square plus az square. So this is the magnitude, right? Now a very important term is there, that is called the direction cosine. What about the direction cosine? Direction cosine of vector A. How do we evaluate it? The direction cosine. You can see this vector A is making some angle with x-axis, it is making some angle with y-axis, and it is making some angle with z-axis. So let's denote these angles to be alpha, beta, and gamma. So let's say if A makes an angle of alpha, if A makes angles, the three angles are there, so it will be angles. If A makes angles of alpha, beta, and gamma with x, y, z axis respectively, then the direction cosine of A is given as, how do we write the direction cosine? So you can say Ax is nothing but A cos alpha. We can say Ay, the Ay is this much. So on this axis, if you want to represent, so it is like this. Okay, now it is same. This much portion is nothing but Ay. So Ay is A cos beta, and on the other hand Az, although it is saying this much, so this is equals to this much, right? So this much portion is your Az, and that is why we can write the direction cosines of A is, we write L is equals to cos alpha. This is direction cosine, and what is the value? You see Ax is equals to A cos alpha, so Ax upon A. A is what? A is the magnitude of the vector A. Similarly M we write cos beta, that is Ay upon A, and N, this one we write cos gamma, and this is nothing but Az upon A. And these direction cosines L, M, N, these are direction cosines. Direction cosines of vector A. These direction cosines follow this property, and this property you should remember that if you take the square, L square, M square, N square, they will give you 1. This one needs to be remembered. In your numerical question, this formula may be utilized. And you see, we can also express these components Ax, Ay and Az in terms of the direction cosine. So you see, if you write Ax, we can just simply write it La. Okay, now. So if I just express the vector in terms of the direction cosine, how do you write? So if I write A cap, let's say we are writing A cap, so we can write, you see, Ax by A I cap plus Ay by A j cap plus Az by A k cap. So we can we not write it in this way, L I cap plus M j cap plus N k cap. So in this way you can express the unit vector along A in terms of the direction cosines. So this is the concept of direction cosine. I hope you understood. And some fundamental things which you already know, but you should keep in mind. The 3 unit vectors I cap, j cap and k cap. So you will take a cyclic rotation like this, and these unit vectors follow certain properties, like I cap cross I cap if you take, or if you take j cap cross j cap, because these are the same vectors, so angle between them is 0 degree, so the value will be, the cross product value will be 0. And on the other hand, if you take consecutive vectors, I cap you take, then you take j cap, what it will give you? It will give you k cap. J cap and k cap if you take, it will give you I cap, and if you take k cap and I cap, it will give you back j cap. So in this way it works. And one thing we have already discussed, but let me tell you, if you have two vectors, then they will be called collinear. If you have two vectors, they will be called collinear. Collinear means these two vectors are lying on the same line. Let's say I am taking this one vector and this one another vector, and they are lying on the same line. So let's say this is vector A, this is vector B. So two vectors will be collinear. Two vectors A and B will be collinear if you see A and B are along the same direction, so the angle between them will be 0 degree or phi. So two vectors A and B will be collinear if the cross product A cross B, this should be 0, sine 0 is 0. So sometimes question may come based on this formula, so that is why we are giving you this. So the vectors may be parallel or anti-parallel. Okay, how do you determine whether they are parallel or anti-parallel? If you see the two vectors are like this, they are parallel, and if you see these vectors like this, they are anti-parallel. So in both the cases, they are collinear, lying on the same line, but this condition will be satisfied for both of them. Okay, so here angle is 0 degree, here angle is phi. Let's move on. We go to the scalar triple product. So few definitions which you should know, because those things come in your examination. So let's talk about the scalar triple product. Scalar triple product basically the product of three vectors A, B, C, and you see when you take the scalar triple product, you get a scalar. So scalar triple product of three vectors A, B, C is defined as A dot B cross C. And how do you write the value? You write the components of A, that is A1, A2, A3. Then you write the components of B, B1, B2, B3. Then you write the components of C, C1, C2, C3. And you take the determinant, you get the value of the scalar triple product. The scalar triple product is represented by writing the vectors in a third bracket, A, B, C. Right? Now they follow, these scalar triple products follow certain properties which we will talk about now. So you see A dot B cross C, this vector will be same as B dot C cross A. So in each time, if you remember this one, A, B, C. So A dot B cross C, now you take B, so B dot C cross A, now you take C, C dot A cross B. So values will be seen, all these three values. In this notation, how do you write it? You write A, B, C. How do you write it? B, C, A. And how do you express this one? C, A, B. Now the scalar triple product is used to denote the volume of a rectangular parallelipiped. Okay. If you know the three sides, and the three sides is designated by the three vectors A, B and C, then the volume of this parallelipiped will be given by the scalar triple product A dot B cross C. So volume of a parallelipiped having A, B, C as congruent edges. So you can see A, B, C, they are congruent edges. Then the volume V will be expressed as A dot B cross C. So it is similar to writing this B dot C cross A. Now volume cannot be negative, so we have to keep a mod symbol. So modulus of A dot B cross C. So in your examination, question may come in this way, that you will be given some vectors A, B, C, and you may be asked to find out the volume. So find out the volume enclosed by the vectors, 3 vectors in this way. Then you can have to utilize this scalar triple product. Actually, you have to understand what formula we have to use. If you do not have the concept of these things, then you will not be able to tackle the problems. Now, using scalar triple product, we can also define the coplanarity. Like if you are given 3 vectors, how do you say that whether they are coplanar or not? To check coplanarity, we can use this scalar triple product. So if A, B and C are coplanar vectors, then we can write A dot B cross C equals to B dot C cross A equals to C dot A cross B. This is equals to 0. How do understand this? Let's say we are taking this in this way. Let's say I am giving you 2 vectors. One vector is like this, another vector is like this. Okay, let's say this vector is vector B, this vector is vector C. So obviously the direction of B cross C will be along this. Now if our vector A should also lie on this plane, okay, if our vector A should also lie on this plane, what criteria it will satisfy? So the angle between A and B cross C, you see this B cross C is perpendicular to both B and C. B and C is lying on this plane. So obviously the angle between B cross C and A, this angle will be 90 degree. And if it is 90 degree, and if you take the dot product, cos 90 is 0. That is why this is the condition of coplanarity. I hope you understood. So this is sufficient for the scalar triple product. Let us now go for the vector triple product. These are small thing, but for the sake of completeness we have to cover. Vector triple product. Vector triple product is defined for 3 vectors, and ultimately it gives you a vector. So vector triple product of 3 vectors A, B, C is defined as A cross B cross C. So this is the usual formula, BAC minus CAB, B into A dot C minus C times A dot B. So this is the formula we have for vector triple product, and it also follow a property, an important property, A cross B cross C. If you remember this one, then that will be easier for us to write the cyclic thing. A cross B cross C, plus B cross C cross A. You have taken this C cross A. Then we will start with C. So C cross what left? A and B. So in this way, if you write, then it will be easier for us to remember. So the product, the sum of these vector table products will be 0. Okay, so the theory part is done. Let us now quickly go to some simple problem so that you understand the thing more clearly. Chalo. Okay, let's go for a problem. For what value of m the three vectors A I cap minus j cap minus 2k cap B is equals to 3 I cap plus 5 j cap plus 6 k cap C is equals to minus I cap plus 4 j cap plus m k cap will be coplanar. So you are given 4 options. Option A 13 by 2, option B 7 by 2, option C 5 by 2, and option D 11 by 2. So how can you solve this particular problem? For what value of m these three vectors will be coplanar? So we have already given you the condition of coplanarity. So if three vectors are coplanar, then their scalar triple product should be 0. Okay na? So if A, B and C are coplanar, then we have A dot B cross C, this is equals to 0. Or you see, how do we write the scalar triple product? We write the components. So component of A is 1 minus 1 minus 2, 1 minus 1 minus 2. Here it is 3, 5, 6. Here it is minus 1, 4 m. This value will be 0. So let's calculate. So we have 5m minus 24 and minus 1 is there, so it becomes plus 1. So 3m plus 6 minus 2, 12 plus 5. 5m plus 3m, 8m. Minus 24 plus 6, minus 18, minus 20, okay, minus 18 and minus 34. So हो गया ये 52. If it goes to the right side, then m becomes 52 divided by 8. So 4, 13, 13 by 2. Option A is matching. Okay. So in this way you can solve this kind of problem. Let's move on to the next problem. The next problem is looking like this. If any vector, let's say x equals to I cap cross A cross j cap plus j cap cross A cross j cap, इसको I cap करो, प्लस k cap cross A cross k cap, then x can be expressed as options are 0 vector, option B vector A, option C 2A vector, option D none of this. How do you solve this problem? So x is given as I cap cross A cross I cap. So how do you write it? We can utilize the formula of this vector triple product A cross B cross C. This is the vector triple product. So B into A dot C minus C into A dot B. So you can utilize this formula. So x will be, here B is A, you see, if you consider the first one, here B is equals to A, so it becomes A into A dot C means I cap dot I cap minus C is I cap, C into A dot B, I cap dot A. So in a similar manner we can write for J cap. And we can write for K cap as well. Okay, so in this way we can express this. I cap dot I cap, we have already told you what is this value. This is value, this value is 1. Okay, so A minus A dot I cap means the x component of A, so that is AX and this I cap plus A minus AY J cap plus A minus AZ K cap. So 3 A's are coming, that gives you 3A, and this AX I cap plus AY J cap plus AZ K cap, that is giving you vector A. So 3A minus A is 2A. So option C is the correct option. Okay, let's move on to the 3 things we'll be talking about: gradient, divergence and curl. So first we'll talk about gradient. How do we define the gradient? Gradient is defined for a scalar function. So let's define this. So we are taking it as a detailed course, so we'll be also writing few lines so that you get a complete thing. So gradient of a continuously differentiable scalar function phi of x, y, z is defined as how to define? We define it as grad phi. Grad is an operator. It is written as del x I cap del y j cap del z k cap, and this is phi. So we write it as del phi by del x I cap del phi by del y j cap del phi by del z k cap. So this is the primary definition of the gradient. Here we have this grad, which is called the gradient operator, Nabla operator. Del x I cap del y j cap del z k cap. So this is the Nabla operator or del operator. This has got various names: del operator or grad operator, or sometimes it is also called Nabla operator. Now let's quickly write the physical interpretation as well. This is not important for your NET exam purpose, but may be helpful in interviews. Interpretation, physical interpretation. So if you talk about this grad phi, what does it basically represent? If you consider a scalar surface like this, so let's say this is phi of x, y, z. Then grad phi basically represents a vector perpendicular to the surface at some particular point. Means at this particular point, if you draw a tangent like this, then you see this gives you the direction of grad phi. And if you specify some point, then this grad phi is evaluated at this particular point. So what basically it represents? You see del phi by del x, del phi by del y, del phi by del, and this direction is this. So it basically represents the change along the normal direction. Okay. So the magnitude of gradient of phi at any point, let's say P, whose coordinates are x, y and z, is equal to the, you see del phi by del x. If you have, let's say, del x by del t, what does it mean? It means rate of change of x, time rate of change of x. So in a similar manner, del phi by del x is equal to rate of change of phi with respect to x. So the same kind of thing is applicable here. So the magnitude of gradient of phi at any point P, x, y, z is equal to the rate of change of scalar phi with distance, because as you go along this, so we are basically taking the rate of change along x, along y, along z. So it is basically the distance, right? The rate of change of scalar phi with direction with distance, I told no, with distance along the direction normal to the level surface. So this is the level surface, you can see, and this is the normal. This is the level surface, and the change happening along the normal direction. This. So this is the physical interpretation of gradient. One other thing you write, note. The direction of grad phi is that along which the rate of change of phi is maximum, and obviously where the rate of change will be maximum, obviously normal direction. You see, if I have a function, I'm giving an example. Let's say the function starts from here. If you follow a path like this, so the rate is not so much. If you take this path, you see the rate of change is higher. If you take this one, it is higher. If you consider like this, here it is like this. So when it will be maximum? When you consider perpendicular, then it will be maximum. So the direction of grad phi is that along which the rate of change of phi is maximum. So I hope you understood. Now here we are using a term called level surface. What is that? What is a level surface? Okay, look at this. This thing I was showing in the picture. This was the phi function, phi of xyz. At any particular point you have taken and you have drawn this tangent plane. Then grad phi basically denotes this. So at each point of the level surface, the value of the scalar function phi of xyz will be same. So you get the direction grad phi. Now if you want to find out the unit vector along this direction, unit vector along the perpendicular direction, how do you express it? You already know it. The vector and its divided by its magnitude. So that will give you the direction, unit vector along the perpendicular direction. See, this is the unit vector along the perpendicular direction. Now let's talk about a directional derivative. It's a simple thing, directional derivative. In alternative language you can understand it is like derivative along some particular direction. Let me give you first an example. Like if you have a vector A, let's say, if you want to find out a component along any arbitrary direction, let's say n cap may be anywhere. How do you calculate the component of A along n cap direction? We take simply the dot product, right? So this is the component of A along n cap direction. This is the straightforward rule. Now directional derivative means you are taking the component of a derivative along some particular direction. Okay, so let's define this. Directional derivative of A, or directional derivative of phi in the direction of A is defined as, so you just simply compare with this. So what thing we are defined? We are defined the derivative of phi. So derivative of phi, it is basically represented by grad phi. Okay? So its component along the direction A. So we will write simply grad phi dot A cap. Okay, na? So this is what directional derivative is. So grad phi and unit vector A is like vector A divided by modulus of vector A. We can also write, look, this modulus of vector A is written in this way also. Just if you keep simple A like this, not bold, then it represents the magnitude of this vector A. Okay, so let us now go for some problem so that you understand it better. Okay, look at this problem. The direction grad f for a scalar field this at the point P112. So simple problem, as you are learning it from the very basic, from the very beginning. So you can give it a try. You have to just find out the direction of grad f. Okay. So first of all, you need to calculate grad f, then you can find out the direction. So what will be the value of grad f? Del f by del x I cap plus del f by del y j cap plus del f by del z k cap. So del f by del x I cap is equals to, you see here x will come, here minus y will come, x minus y I cap plus del f by del y. So minus x is coming, and what about del f by del z? Only z is coming. So you want to find out the direction of grad f, means you have to find out n cap. So what is the value of n cap? That nothing but grad f divided by modulus of grad f. So this is equals to nothing but x minus y I cap minus x j cap plus z k cap divided by, if you want to take the modulus, I told you, you have to take square of the components and you have to just add them. So x minus y whole square plus x square plus z square. And when you specify the point, means n cap where at 1 1 2, means at x equals to 1, y equals to 1, z is equals to 2, then it becomes how much? This is 0, so this is minus j cap plus 2k cap divided by root over x square plus z square. So 1 square plus 2 square, and this is 0. So minus j plus 2k cap divided by root 5. So option B is matching. Okay, so I hope you understood. So this is a simple problem. Now the problem can be made little bit complicated. How? The process is simple, but the scalar field or the scalar function phi, that may be given little bit complex. So as you can see in the next problem, Look at this problem. This becomes little bit complicated, but the process is simple. The unit normal vector, basically it is asking about n cap of the point this 1 by root 3, 1 by root 3, 1 by root 3 on the surface of the ellipsoid. X square by a square plus y square by b square plus z square by c square equals to 1 is. So the process is simple. Process is same. Can you do this problem? Guys, you can join the dedicated WhatsApp group for physics of English only. You can join that. It is given in the description. The link is given in the description. So let's try to evaluate it. So first of all, how to determine phi? So whatever expressions you are given, you will take this one on the left side, and the first way, actually this thing you have to find out. It is represented pictorially beautifully. Let's try to evaluate the solution now. So here, what is phi? Phi, you see, x square by a square plus y square by b square plus z square by c square. 1 was on the right side, we are taking it on the left side, so it becomes minus 1. So in this way phi is defined. Once phi is defined, we can easily calculate n cap, that is grad phi, upon modulus of grad phi. This kind of problem may come in your examination. So first of all, evaluating grad phi is pretty simple. I am not writing all the formula, I'm just you can directly calculate it. Okay. So what will be the value of grad phi? You see, 2x will come from here, and a square is a square, so 2x by a square I cap plus 2y by b square j cap plus 2z by c square k cap. Simple. Now if you calculate the grad phi at the given point, 1 upon root 3, 1 upon root 3, 1 upon root 3. Just put the values. So what do you get? 2 by root 3 a square, 2 by root 3 b square, 2 by root 3 c square. In this way you get. Now if you take the modulus, as I told you, देखो, in the very beginning I gave you the formula how to find out the magnitude. Take the components, square them and add them all. This is what you have to do. 4 by 3a to the power 4, 4 by 3b to the power 4, 4 by 3c to the power. Obviously this is evaluated at this point. One by root 3, 1 by root 3, 1 by root 3. Then we have the mod. So we can take this 4 by root 3, 4 by 3 common, so it will become as 2 by root 3, right? And in the denominator, so under root everything will be there, a to the power 4, b to the power 4, c to the power 4. So this is b to the power 4, c to the power 4 plus a to the power 4, c to the power 4 plus a to the power 4, b to the power 4. This is the thing it will come. So kind of homogeneity is there, so it is easier for us to calculate. And now we can calculate this unit vector by taking the ratio of grad phi and modulus of grad phi. Okay, I am just denoting this as p. Okay, because my writing this multiple times is taking too much time. So it is like grad phi evaluated at p, grad phi evaluated at t magnitude, right? So you see, if you take the ratio, this 2 by root 3, 2 by root 3, it is cancelling, and here it will be a square, b square, c square, and every time you see a square will be cancelled, so b square, c square will remain, b square is cancelled, so a square, c square will remain, c square is cancelled, so a square, b square will remain. So b square, c square I cap plus a square, c square j cap plus a square b square k cap, right, divided by this thing will come in the denominator, root over b to the power 4 c to the power 4 a to the power 4 c to the power 4 a to the power 4 b to the power 4. Okay, and this is matching with option D. So this kind of problem may be given to you and you can easily do this. चलो मैं एक प्रॉब्लम दे देता हूँ. Let's give you a problem as homework. In the last class also I gave you one problem as homework. You can join the WhatsApp group, given the link is given in the description, and you can send us the solution. Okay, let's take this problem as homework. So similar problem, I have already solved 2 and it's your turn to solve it at home. So take it as homework, simple problem. The equation of a surface of revolution is z upon root 2 is equals to plus minus root over 3 by 2 x square plus 3 by 2 y square. The unit normal to the surface at the point A is. So exact same problem, only thing is this. So don't get frightened by looking at this expression. What you do, you take square on both sides. So if you take squares on both sides and simplify, then you will get equation. Then you will get an equation. Then you write them at phi is equals to that. So that will be your expression of the scalar function phi. And once you know that, the process is straightforward again. N cap grad phi upon modulus of grad phi. Okay, so we will try at home and you have to find it at, you see, root over 2 by 3 0 2. So you will get option B to be correct. I am giving you the answer key. Option B. So you will try to do it at home. One last thing I would like to do today, then we will wrap up the session. Sorry guys. The next thing which we are going to discuss is a very important thing. That is tangent plane and normal to the level surface. We have discussed it multiple times. Let's discuss one more time because we are doing everything from fresh now. So you can give the heading tangent plane and normal to the level. So this is very easy topic. If you have understood till now whatever we have taught, then understanding this one is like taking water. Chalo. So first of all, level surface, let's draw a level surface. Let's say this is a level surface, right? This level surface is denoted by phi x, y, g is equals to some constant c. Now if I consider a particular point, let's say P, whose coordinate is given as x, y, g, then what is the tangent plane at this? So before going to the tangent plane, we need to understand the tangent line. Okay now. So tangent, this is the tangent line. Tangent plane is like if you just keep many lines one after other, then it will give rise to a plane. What do I mean? If you do it in this way, then this becomes a plane. Okay, so you have to find out the equation of this plane. You consider a bowl and a cardboard is placed on the top of it. Now you have to find out the tangent plane equation. So if you see, if I draw, okay, let's draw it afresh because the picture is not giving us what we are intending to show. So let's first draw. You understood the concept, right? So let us first draw the plane so that it looks like it is a tangent plane. Now let's target to draw the level surface. kind of reverse engineering is happening. Okay, so this is the surface phi of xyz equals to c, and this is the point, let's say P xyz. Now it is, I think, clear. So what if we draw the perpendicular? So if you draw this perpendicular, then what it will give you? It will give you the direction of grad phi, right? Now if I take any point on the plane, this is the plane, this is the tangent plane. What will happen if I take any point? You can take the point here, here, any arbitrary point. So arbitrary point, so arbitrary coordinate will be there, x, y, j. So these are capital, okay, to differentiate it. And if you join these 2 points, so you get a vector, right? Let's say this point is denoted as r. So obviously this PR and this grad phi, they are making an angle 90 degree. So they will satisfy this condition that grad phi dot PR, this should be 0, cos 90 is 0. Or the reverse thing is also true. You can also express it in this way. You can express it, let's say PR dot grad phi equals to 0. Now you consider these are the points P and R. So they are denoted with respect to some arbitrary reference point. So let's say the origin is here. Okay. So the position vector of P is this. Position vector of R is this. You can consider it in this way. So this is the position vector. Let's say this is R, small r. Okay. And this is capital R. So what will be this? This will be capital R minus small r. You can use vector law of addition to verify this. You see, if you add r and this, so you get back capital R. And if the coordinates of 2 points are given, we can easily find out the vector, right? So it is nothing but capital R minus small r dot grad phi equals to 0. Now capital R minus small r, how do you calculate? By taking the difference of their coordinates. Okay, I am just writing it, x minus x I cap plus y minus y j cap plus z minus z k cap. This is the vector r minus r dot grad phi. Grad phi you already know, del phi by del x I cap, del phi by del y j cap, del phi by del z k cap, right? Now if you take the dot product, what do you get? You get x minus x del phi by del x plus y minus y del phi by del y. And you can pose your question, okay? Don't just listen. If you have any question, you can ask, or if everything is clear, then that is okay. Actually, these things are very simple. There should not be any question. So this equation basically gives you the equation of the plane. This defines the equation of the tangent plane. So this is the ideal theory. Now in your examination, you may be given the question in different forms. One such question which came in December 2011, we will try to do. Let's go for the problem. Give it a try. The equation of the plane that is tangent to the surface xyz equals to 8 at the point 1, 2, 4 is. Give it a try and let me know the answer. Okay, let's try to evaluate this problem. First of all, the surface is given to be xyg is equals to 8, and the point where you have to find out the tangent, there is 1, 2, 4. Okay, so you can imagine that a tangent plane is there like this. So you can imagine in this way, this is the tangent plane. So you have to find out the equation of this tangent plane. So if I consider this point to be P, this point to be P, and let's say another point is there on the tangent plane, let's call it T, whose coordinate is x, y, z, we do not know. Then you join it, and the perpendicular you already have, that is grad phi. Grad phi evaluated at this 1, 2, 4. So the condition will become grad phi evaluated at 1, 2, 4. So vector dot this TP or PT, whatever you say, will be 0. This is the thing, right? Sorry, kya kiya? First of all, grad phi. What is grad phi? What is phi? First of all, phi is nothing but x, y, g minus 8. So grad phi will become, you see, yz I cap plus zx j cap plus xy k cap, right? This is evaluated at 1, 2, 4 dot TP. TP, as I told you, you have to take the difference in the coordinates. So x minus 1 I cap plus y minus 2 j cap plus z minus 4 k cap. This should be equals to 0. Now put the value of x equals to 1, y is equals to 2, and z is equals to 4. Okay, so yz is 8, right? So 8 I cap plus zx 4 j cap plus xy is 2 k cap multiplied by this one, x minus 1 I cap plus y minus 2 j cap plus z minus 4 k cap. This is equals to 0. And if you take the dot product, what do you get? Let's give second bracket. So 8 times x minus 1 plus 4 times y minus 2 plus 2 times z minus 4, this is equals to 0. Now you take 4 common, so 4 times x minus 1 plus 2 times y minus 2 plus z minus 4. If you simplify it even more, what do you get? You will get 4x plus 2y plus z is equals to minus 4 minus 8 plus 4, so 12, minus 12 plus 12. So 4x plus 2y plus z is equals to 12. So in this way you evaluate the solution. Okay, so I hope you have understood everything. In this lecture we have covered the very fundamental thing of vectors. On the next day we'll try to continue from here, and the next class we'll try to take on Monday 8 p.m. Monday 8 a.m. Okay, Sunday will be off. So see you Monday at 8 a.m. again. And if you have not downloaded our physics application, you can download from the Play Store. The link is given in the description. You can also join Telegram group and WhatsApp group. All the links are given in the description. Okay, so this is all for this video, guys. If you are new to this channel, so please subscribe the channel and don't forget to press the bell icon. Thank you. See you in the next class. Bye bye. Take care. Hello, guys. Good morning to all of you. Welcome to Physics of English. Once again, we are here with another lecture. So without any further ado, let's start. Good morning. Okay, so I think audio, video, everything is all right. So we are directly coming into the point. Today's lecture title is Vector Analysis Part 2. So in the last two lectures, we covered dimension analysis and we started vector analysis. So we have done the introduction part of the vector analysis. Today, in this part, we'll be going forward one step ahead. And guys, if you have not downloaded our physics of application, you can download it from the Play Store by searching this name, or you can also scan this QR code to get the application. And before I continue, let me tell you guys, if you are appearing for GATE examination, you can go for this GATE 2024 physics mock test series. Basically, full test series is available, and as well as only full length mock tests are also available. This mock test has complete and detailed solution. So in a separate PDF form, you will be given the solutions, and you can attempt the test in any device, on mobile, on desktop, on tablet, everywhere you can attempt the test. So you can purchase this. The link of everything is given in the description. So without any further ado, let's start. So in the last class, we started discussing about gradient, divergence and curl, and we covered the gradient part. Let's start with the divergence. These things are very simple, but as we are doing this course from the very beginning, so this is equally helpful for a beginner as well as an advanced learner. So let's start with today's topic. So we'll start with divergence. What is the meaning of this term divergence? Divergence basically literally means that to expand, right? So the measure of divergence gives you how much some vector field is expanding. This is the literal meaning of divergence. Now let's try to define it mathematically. Okay. So mathematically, how do you define this particular thing? So divergence of a continuous differentiable vector point function. What does this term continuous meaning here? Continuously differentiable, it is like if you take one derivative, first derivative, it will exist. You take second derivative, it will also exist. You take third derivative, that will also exist. So it is continuously differentiable. So divergence is defined for a vector, and what you get ultimately, you get a scalar. Okay. So divergence of a continuous differentiable vector point function V is specified in a vector field. So we are basically defined it for a vector, right? This you have to remember. This definition are very trivial, but we have to do it. Divergence of V. So here the grad operator we already know, del x I cap plus del y j cap del z k cap, and V is a vector function, so it will have three components: Vx I cap, Vy j cap, Vz k-cap. So for the time being, we are doing it for the Cartesian coordinate, and in the upcoming lectures we will also look this expression of divergence in different coordinate system like spherical polar coordinate, cylindrical polar coordinate. So you see I cap and this I cap, so that makes one del Vx upon del x plus del Vy upon del y plus del Vz upon del z. So you can see this is purely a scalar quantity. So divergence of a vector function is a scalar function. Okay, now let's quickly talk about the physical interpretation. Physical interpretation is quite obvious from its name. Physical interpretation, you can predict from its name. It basically represents gives you a measure like how much the vector field is expanding. We'll also take the help of some picture to understand this thing. For the timing, let's write it that divergence at any point, divergence is defined at any point, divergence of V at any point, let's take an arbitrary point P whose coordinate is x, y, z, is defined as the outward flow. Okay, it is defined as the outward flow or flux, outward flux of the vector field V, per unit volume enclosed by the point, enclosed by an infinitesimal closed surface surrounding at P. You can understand it in this way. You have a vector field, so any point, and you have to consider the outward flux over some infinitesimal closed surface surrounding the point P. So this is the physical interpretation of divergence. Look, you can get different values of this divergence. You can get the value of the divergence, you can get it to be positive, you can get it to be negative, you can get it to be 0. So divergence is only giving you the magnitude, the value. It doesn't give you the direction. It only gives you the value. It doesn't give you the direction. It doesn't give you the direction of the vector field. So that is why this divergence is a scalar quantity. They are very simple thing. I hope you understood. Let's take an example to visualize this thing in more detail. Look at this picture. Okay, this is an example of the vector field. Okay, this is drawn based on some vector field, maybe with some mathematical software. These vector fields are shown. As you can see, the arrows represents maybe the magnitude. As you can see, it is expanding. So it is an outward flux of the vector field. Imagine that the vector field F pictured here gives the velocity of some fluid. It appears that the fluid is exploding outward from the origin. Okay, so in the, at the origin it is originating and it is expanding outward.
This expansion of fluid flowing with velocity v is captured by the divergence of f, which we denote divergence of f. And this divergence is positive since the flow is expanding. So I give you three cases in the last slide, that it may be positive, it may be negative, or it may be 0. So based on this, it has got three names. When it is less than 0, divergence is less than 0, it means the flux are coming towards a particular point. Okay, that's you have to keep in mind. When the divergence is negative, it means the flux is coming, incoming flux, that is called sink field. And when it is positive, it means the flux are coming, flux are going outward like this. This is called source field. And when the flux are not either expanding, neither expanding nor compressing, then that case is called solenoidal. So sometimes you may be given some question like for what value, maybe b is given, some vector function is given in terms of some unknown quantities, and you may be asked for what value of that unknown quantity the vector field will be a solenoidal field. Then we have to employ this condition. This condition is particularly the most important condition among these three. And with a practical example also you can understand this divergence concept. Let's say we have a water tap, water is coming, so where the water is just falling down. So from that you can understand that if you look at the direction, let's take red color. So here at this position the flow of water is outward. So here this is a source field, so grad v is greater than 0. Okay, now you see in the sink, why name sink? Because in the sink you see water flow is going inward through this sink and going out. So that is why here divergence of v is less than 0, and that is why it is called sink field. And if you go away from this water flow, here you see, so this kind of thing, neither expanding nor compressing. So this is the example of solenoidal. So with a real life picture you can understand this phenomena beautifully. Now there are some formula related to this divergence which you should note. Two formula I will be giving you. Like if you consider the divergence of the sum of two vector functions, let's say one vector is u, another vector function is v. So divergence of u plus v, this will be distributive in nature. So divergence of u plus the divergence of v. On the other hand, another formula is there which you should note, that if you consider the divergence of some vector function with a constant multiplier, let's say alpha is a scalar quantity or constant, then what will be its value? Let's say this the usual notation is u, small u is a scalar, this u is a scalar here. So this will be gradient of u and the divergence with v, and dot product with v, plus u times divergence of v. So these two formula you need to keep in mind regarding the divergence. So I think you have understood divergence pretty well. If you have any question you can ask. Let me give you an idea about the curl after that. Curl is also very simple thing. Curl, what is the literal meaning of curl? Curl means something which is rotating. So what does curl represent? Curl represents the rotation of the vector field. Curl is also defined for a vector. So let's define curl of a vector field. How to define? So as usual, curl of a continuous differentiable vector at any point. Okay, curl of a continuous vector point function V is defined as, how to define this curl? Curl of V, right? So this is Nabla operator, del del x I cap plus del del y j cap plus del del z k cap, and this is Vx I cap Vy j cap plus Vz k cap. Now how do you write it? You know it very well. So we write it in a third bracket. We first write the component of this. We write I cap, j cap, k cap. Then we write the component of this Nabla, that is delta x, del del x, del del y, del del z. Then we write the components of V, which are Vx, Vy, and Vz. So what does it basically measures? The curl measures the rotation. Curl measures the rotation of vector field. Okay, and what about the direction? Because you see, curl of a vector is a vector. Previously we defined divergence. Divergence of a vector was a scalar, but here curl of a vector is a vector, so it will definitely have some direction. What is the direction? And the direction of curl vector is the direction of rotation, each along the axis of rotation. Is along the axis of rotation. As you can see in this figure, this represents the direction of curl, that is axis of rotation. Now as I told you that this curl represents the rotation of vector field. So if you get that the curl is 0, what does it mean? There is no rotation. So if we have curl of some vector equals to 0, then that vector is known as irrotational vector. Irrotational. And obviously if the value of curl is not equals to 0, means it has some rotation, then V will be known as rotational vector. Simple. Now you see, if curl of V is equals to 0, we can write a special thing. We'll talk about it. What about this thing? We can write that V is written as gradient of some scalar function. If curl is 0, we can write that vector function as the gradient of some scalar function. This one is very important. Many a times you will see this, and question may come from this fact also. Now here also we have some vector identities which we should be talking about. The vector identities, firstly, if you have, let's say you are calculating the curl of sum of two vector functions, let's say u and v, then what do you get? It is again distributive in nature, curl of u plus curl of v, right? And another similar formula which we did in divergence, curl of, let's say the scalar is multiplied u with the vector function v, then it will be u times curl of v plus, so you see this formula are very simple, similar, gradient of u cross v. And if you just compare with these two formula, it has a strange similarity, like strong similarity. U into divergence of v, you see, and here you have u into curl of v, then gradient of u cross v was there, and here you see gradient of u dot v. So if you remember one thing, then from the analogy you can write the other thing. So this formula may be utilized many times. Look, this mathematical method is the fundamental thing. In future you will be studying electromagnetic theory and other subjects as well, mainly electromagnetic theory. In electromagnetic theory these concepts will be heavily used. So if you are not clear here, then you will find electrodynamics very difficult. So if your mathematical part is strong, especially the vector part, then your electrodynamics numerical part will be equally strong. Okay, so somehow try to understand this vector algebra and vector calculus pretty well, so that you find the electrodynamics very easy. Otherwise electrodynamics will hit you hard every time. Okay, let me give you one problem based on this. So this problem came in December 2014, very simple problem. This kind of problem used to come previously. Nowadays also some questions come which are extremely easy. Okay, let R denote the position vector of any point in three-dimensional space. R is the magnitude of R. Then which of the options is correct? How will you solve this problem? So you are given the R vector, which is the position vector. So we can write it as x I cap plus y j cap plus z k cap. So if you evaluate the divergence of this vector R, then this is del x of this function, so that is 1. Okay, so it is like del x by del x plus del y by del y plus del z by del z, thing like this. So this is nothing but 3. And if you calculate curl of R, what does it give you? I cap, j cap, k cap. We write the component of del x, del y, del z. We then write the component of R, x, y, g, and you see this is basically 0. So option D is matching with our answer. Okay, let's move on. Okay, one formula, one or two formula I would like to give you here, important formula. Important note. Number 1, curl of gradient of phi is 0. This is one thing. Mathematically speaking, curl of gradient of phi equals to 0. Second thing, a divergence of curl of A is again 0. Mathematically, divergence of curl of vector A equals to 0. Okay, and here one formula you should keep in mind, like if I give you curl of A, this kind of formula you will encounter in electrodynamics, then this will be written as gradient of divergence of A minus grad square A. Fourth one, this one is an important formula. If you have a constant vector, for a constant vector, let's say A, gradient of A dot R, this value will come out to be A only. And if you take the curl of A cross R, this will give you 2A. This can be proved very easily. There is not an issue. Okay, so let's go for a problem. Look at this problem. If a force F is derivable from a potential function B of R, where R is the distance from the origin of the coordinate system, it follows. Again, this came in GATE 2011. So related problems should be done from all different kinds of exam, different types of exams. F is derivable from a potential function V of R. What does it say? F is derivable from a potential function grad of V. So we know which is F is equals to minus grad V, already we know. Then which of the following is correct? So if this is given, actually F is a derivable function of potential. So if we calculate curl of F, what does it give you? Let's keep minus aside. Curl of grad V. So what is this? Curl of gradient. What did I tell you? Curl of gradient is 0. So this value will come out to be 0. Means option A is 0. Here we have used the logic that curl of a gradient is 0. So option A is coming out to be correct. Let's move on. A very important calculation is there. Let's say R is the position vector. So how do we write? We write in terms of the position coordinates x, y, z, let's say. So what will be the magnitude? Magnitude will be R. How do we write the magnitude? Root over x square plus y square plus z square. In this way we write. Then we have to show that if you take the gradient of r to the power n, it should give you n r to the power n minus 2 times vector r. So this thing, how will you prove? So proof कैसे करें? Let's go for this proof. So it is like finding gradient of r to the power n. R is the magnitude of this vector r. So we can write it as del x of r to the power n I cap plus del y r to the power n j cap del z r to the power n k cap. Now let's only consider the first one, because the second and third term are similar to first one. So we are dealing with one term first, then using the analogy we can comment on the other two. So del del x of r to the power n, if r is equals to this x square plus y square plus z square to the power half. So to the power n means basically it becomes n by 2. And if you take the derivative with respect to x, n by 2 x square plus y square plus z square, this will be n by 2 minus 1, and derivative of x square is 2x. So this gives you nx, and you see what does it give you? It gives you n minus 2 by 2. So can we not write r to the power n minus 2, because r is equals to x square plus y square plus z square to the power half. So this n minus 2 by 2 becomes r to the power n minus 2. So similarly for del del y r to the power n, what you gonna get? Ny r to the power n minus 2, and if you calculate del del z, what you gonna get? Nz r to the power n minus 2, and hence gradient of r to the power n, this will become, look, they in the first expression sum of these three quantities, and n r to the power n minus 2 is common in each term. First term, what is that? X I cap, plus second term y j cap, third term z k cap. This is nothing but r, so this becomes n r to the power n minus 2, and this is vector r. So in this way we prove that gradient of r to the power n is equals to nr to the power n minus 2 vector r. So you should remember this result. You may require to use this result directly in your examination. So if you remember this result, then that will be good for you. I am giving you a problem similar to this problem. So hold on a moment. Let's try to understand this problem. The expression Nabla square r to the power n can be written as. So using the last result, we can easily evaluate, we can easily calculate this result. Grad square r to the power n. So we can write it as divergence of, write it in this way. This one we have written from this fact that divergence of let's say phi a is equals to grad phi dot a plus phi times divergence of a. So using this result we can write it. And this becomes, you see, divergence of, and this result we have already derived in the last slide, n r to the power n minus 2 vector r. So let's directly put that value, n r to the power n minus 2 vector r, n r to the power n minus 2 vector r. Now we can utilize this formula again. Okay, so basically this formula is useful. Now you can imagine that this thing is nothing but the scalar part phi, and this r is this vector a. So let's utilize this. So grad phi dot a, so gradient of n r to the power n minus 2 not r plus phi into, so n r to the power n minus 2 divergence of a, that is divergence of r. Okay, now divergence of this means basically derivative with respect to r. Okay, so n into n minus 2 r to the power n minus 3 r cap dot r plus, the gradient gives you some vector, so r cap is the direction of this grad of this scalar function, plus, and you see divergence of r we have already calculated the value of divergence of r. This thing has a value 3, so this becomes 3n r to the power n minus 2. So this is nothing but n into n minus 2, and you see r cap is nothing but r by vector r by r. So vector r cap dot r, what will it become? R cap dot r cap, that will be 1. Okay, so this becomes r to the power n minus 2 plus 3n r to the power n minus 2. So it becomes n into n minus 2, so n square minus 2n plus 3n r to the power n minus 2. So n square plus n, that is n into n plus 1 r to the power n minus 2. Is it clear, guys? देखो यहाँ r cap dot r, it becomes r. ये हुआ ना, you can use this identities here and you will get here r to the power n minus 3 into r, so r to the power n minus 2. So which option is it matching with? It is matching with option C, n into n plus 1 r to the power n minus 2. So if you remember only one result, this one, you can easily evaluate this one. Let's move on. Okay, this problem, very important problem. Let A be be two distinct vector, three-dimensional vectors, then the component of B that is perpendicular to A is given by. How will you solve this? Let's first try to draw the vectors. Let's say B vector is this, A vector is this. This is vector B and this is vector A. So for obvious reason, this B vector will have one component here, okay. So B vector will have one parallel component and one perpendicular component. What does the question ask? Then the component of B that is perpendicular to A. So perpendicular to A is this component, you can imagine, or we can say that this is the perpendicular component of B. So if this angle is theta, angle between A and B is theta, so this is nothing but B sin theta, and if I consider the horizontal component, that will be your B cos theta, right. So here we have assumed that A and B are lying on the xy plane. Assume that A and B lie on the xy plane. Therefore, the component of B that is perpendicular to A is nothing but B sin theta. Now if I assign, let's say this is I cap, this is j cap direction, so perpendicular component is j cap direction, right. Now we have to find out like which of these option is equal to this B sin theta j cap. Four options are given, so which of these options will give us this vector? Okay, let's calculate, like A cross B is there everywhere. In these first two options, A cross B is there or B cross A. So let's find out A cross B, because from A cross B we can easily calculate B cross A. So you know the formula A B sin theta. Now what about direction? Direction of A is I cap, direction of B is j cap. So direction of A cross B will be AB sin theta, I cap cross k cap, that is k cap. Now if I go one step ahead, A cross B, then it will be AB sin theta multiplied by this A, and direction of A is I cap, direction of A cross B is k cap. So I cross k cap. So I have already told you this, to draw this kind of thing, I cap, j cap and k cap. So if you are taking the cross product of I and k, so we are going anti-clockwise, so that will be minus j cap, right. So this is nothing but minus A square B sin theta, and it is j cap. We need to ultimately find out B sin theta j cap. How can we get this B sin theta j cap from here? First of all, this minus needs to be removed. So if I just write A cross B as B cross A, then extra negative sign will introduce. So this negative sign vanish, then A square B sin theta j-cap. Now to get b sin theta j-cap, we need to divide it by a square, and that is why a cross b cross a upon a square is equals to b sin theta j-cap, and that is correctly matching with option A. So in this way you can get a solution of this question. So beautiful question came in CSIR-NET examination. That is why practicing previous year questions are very important. It gives you some really standard problems. Okay. So in this video we have covered gradient, divergence, curl. On the next class we will try to take tomorrow at 8 AM. Next class tentatively tomorrow 8 will be covering a linear line integral. That is very important. Line integral, surface integral, volume integral and related theorems. Related theorems, two main theorems are there, divergence and Stokes, and question may come from this divergence and Stokes theorem. These two theorems are very important for your examination. Okay, so we are stopping here today. And guys, before I stop, let me tell you guys, if you are preparing for GATE examination, you can join this GATE 2024 physics test series. So the links are given in the description. And if you are new to this channel, please subscribe the channel and don't forget to press the bell icon, and try to attend these classes live, guys, because these classes may not be available for a long time. So it is better if you make a habit of attending these classes live. Okay, thank you very much. See you in the next class. See you tomorrow at 8 AM. Thank you. Okay, good morning guys. Welcome to Physics of English and welcome to the class. Today we'll be continuing our discussion on vector analysis. This is the third part 3. If you want to get all the lectures in a single course, you can download or install the Physics Hub application from the Play Store, and you can also visit the website. All the links are given in the description. Today in this video we are going to discuss about these three things: line integrals, surface integral and volume integral. Just hold on a moment. Okay, just let me know if everything is all right, then we can start. This is an important class because a lot of questions can be expected from this one topic of line integral. And you have seen in previous year questions also, a lot of easy questions came from this line integral. So without any further ado, let's start with this line integral. So what do you basically do in evaluating the line integrals? Line integrals basically evaluating the integration of some vector function along some particular line or curve. So if in rough words we can say that. So here what we have some line or curve. For the generalized purpose, we are taking a curve, let's say a curve like this, AB. Okay, and we want to find out the line integral on this curve. So the line integral is defined for a vector function. So let's take a vector function as well. So we are denoting the vector function by f. On this curve, at each and every point, the vector will be defined, right? And how we are defining the line integral, that is the question. Now to get a reference point, we are considering that our origin is situated here. So with respect to this origin, we are measuring everything, and let's consider that the x-axis is along this direction. So we are setting up the coordinate system. Now we are taking an arbitrary point. As I told you, at each and every point we can define this vector function. So we are considering that for the time being we have a point here. Let's call that point to be P. Now to assign the exact position of this point P, we have to define it with respect to the origin O. So let's say the position vector of this point P is R. Okay. So how do you define that? If I draw a line like this, then the position vector we are calling to be R. Now what is the line integral? Line integral will define as the component of f along the tangent to this line. So if this point is P, and if you want to draw a tangent at this point, then how will you, what kind of form will it give? So a tangent will look like this. A tangent will kind of look like this. I'm just drawing it bigger so that you understand. So that is T, let's say. What is T? T is the tangent. So first of all, let us write what we have defined. Firstly, we have defined that this f, obviously we are taking it in a three-dimensional case, f xyz be a vector function and let f of xyz be a vector function and a be a curve. These two things we have defined. Now how to define the line integral? As I told you, line integral of a vector function, this is the basic definition. Okay, this is the line integral of a vector function f along the curve. It must be defined on some curve. For the general purpose, we have taken a curve. It may be a straight line also. Line integral of a vector function f along the curve AB is defined as the integral of the component of f, at this particular point f is acting. Now its component will be there along this tangent. So the integral of the component of f along the tangent to the curve, tangent to the curve AB. Now if I consider all other points, if you consider this point, the tangent will be different. If you consider this point, the tangent will be like this. For this, tangent will be like this. If you consider this point, tangent will be like this. For this, tangent will be like this. So when you integrate all of these components, then you get the line integral. So first of all, let's calculate the component of f along a tangent PT at P. So we are defining it for a single point, then we can consider for the whole curve. And one thing I would like to tell you, this is I have already explained many times. If you have a vector, let's say like this, and you want to calculate the component along some particular direction, we have a vector, let's say A. If you want to calculate the component along a particular direction n cap, then what do? You take the dot product of A and the unit vector along that particular direction. Okay, if vector B is there, so if vector B is there, you have to take the dot product of A with B-CAB. Okay, so this is the general thing. So to calculate the component of F along the tangent at PT, what you have to take? You have to take the dot product of F and unit vector along PT, right? Unit vector along PT. So what is the dot product of F and unit vector along PT? F dot, what is the unit vector along PT? That is given by dr by ds. What is this dr by ds? Dr by ds is the unit vector along the tangent PT. We can write, what does this dr by ds represent? Dr by ds is a unit vector along PT, right? Then we can write the line integral. We can define it as the sum of all the points f dot dr by ds, right? Now this sum is very much close to each other. If you consider there may be millions and trillions of points in between point A and B, so what we can do, we can just convert it into integral also. So line integral is basically sum of these things from the point A to B, from A to B along the curve. So obviously if you consider different paths, let's say if you do not visit the point B along this path, if you choose another path like this or another path, then obviously the line integral will change. We'll consider some conservative, if the vector is conservative, okay, then the line integral will be independent of the path. But for the time being, in general cases, we can say that if you choose different paths, then the line integral should be different, okay, because obviously the tangent at each and every point will be different and all those things. And we define this line integral in terms of the integration. So if you are given any curve, then the curve is represented by C. So integration over some given curve C, f dot dr by ds. So this sum, instead of this using this sum, you can write it in terms of integration in this way, okay. So that is why the ultimate formula for the line integral is written as f dot dr. So this one you have to remember. This is the theory part, but for you, if you only need to remember this part, the line integral is f dot dr. Okay. Now dr, we can write it in different dimension. If you are given a one-dimensional case, let's say, then what will you write? And if you are given two-dimensional case, what will you write? I am writing it here. Let's say dr, depending on the given dimension, let's say in one dimension it will be dx I cap. If you are given in two dimension, so dx I cap plus dy j cap. If you are given a three-dimensional case, so dx I cap dy j cap dz k cap. In this way we can write, okay. Now let me give you An example of this line integral, magnetized bead on a slinky. So this is a good example of giving you the idea of line integral. For this line integral, if you closely look at, if you consider this function to be the function of force, then this line integral will give you the work done. And look at this magnetized bead on a slinky. A slinky is a pre-compressed helical spring toy. So you can see this is the slinky and a magnetic field has been applied here. So this particle will experience some force and it is traveling along this path, along this arc-like curve. Now at t equals to 0, it starts its journey from here, and because of the influence of this field, it is taking up this path like this. Okay. Now at any instant here, the component of different forces are shown here. So at all the time, the force is directed along this direction. If you consider this point also, force will be directed in this along this direction. If the bead is here, then also the force will be acting along this direction. The force direction is same. You can see the lines of force. And at this point, we have drawn the tangent, because for evaluating the line integral, we have to draw the tangent at that particular point. So tangent is drawn here. So the component of the force in the direction of movement is simply the dot product of the force at the point c of t. Here let's say c of t, so function of time, right? Because if you see t goes to 0 here, if you change the time, the bead will be some other position. So the dot product of the force at that point with the tangent vector t of t. If you multiply this component f and t dot product, if you take the dot product, we get the work. F dot t as a scalar valued function that gives work per unit length along the slinky. And that is why when you integrate over the length of the slinky, we get the total work done. And F dot t alone is nothing but the work done per unit length along the slinky. C is the path of the slinky. This integral adds up to the product of f of t, f dot t and distance ds along the slinky, which is the work done. So this is a very good demonstration of the line integral. So I hope you understood the line integral pretty well. Let me just give you few things which you should remember. So you can write them as note. The first one being, as I have already told you, if your f, the function, represents the force, represents the variable force, obviously, variable force acting on a particle along the curve, let's say AB, then the total work done is given by the line integral. Work done for the path AB, A to B, f dot dr. Okay, so obviously it is path dependent. Another case we can consider, if let's say V, a vector, represents velocity of a liquid, then what will this V dot dr represent? Is called the circulation of V round closed curve C. Okay. Now look, two things are possible. One thing is when you are going from A to B, this is one way, right? Now when you are completing a path, if you are closing the path, you are going coming back, so you are making a closed loop. Then instead of a normal integration, we'll write some circle here. Okay, so this is the third point. When the integration is carried on a closed curve, then instead of using this, we use this symbol, right? Now let's specifically talk about the work done thing. Now let's give you the concept of conservative force field. This is very important, question may come from this. Conservative field. As I told you previously also, let's say we have 2 points A and B, and it is we are evaluating the line integral for a vector function along this curve from A to B. Now if you consider different paths, in general the line integral will be different, but when the vector function acting here is conservative in nature, then the line integral will be independent of the path. It means whether you go along this path or along this path or along this path, the line integral value will be same. So what is the criteria for this being time independent, being path independent? That the function, vector function, should be conservative. Now how to identify whether a function is conservative or not? If a vector function is conservative, then it can be written as the scalar of some gradient of some scalar function. Okay, so if you want to write the definition of conservative field, we can simply write a conservative vector field is a vector field that is the gradient of some scalar function. So the well-known example, you know, that if f is the conservative vector field, we know that it can be expressed as the gradient of some scalar function. Okay, so we give a minus sign, so that is case dependent, but in general we can just simply write, if you do not know, if you do not force, if you are writing in general, then it is that vector is equals to gradient of some scalar function. Okay, I hope this is done. Let us consider 2 points. One point is P, another point is Q. Now what will be the work done in taking and moving a point from point A P to point P, from point P to point Q? So work done by a conservative field let's say A in moving a particle from point P to Q will be, what will be the expression? You see, it will be integration from P to Q f dot dr, right? So as I told you, P to Q f dot dr, f can be written as grad of some scalar function if you consider that it is conservative. As I told you, we have already defined it as conservative field, so it can be written as the gradient of some scalar function, phi is some scalar function, dot dr. So what is this value? P to Q, this will become, you see, del phi by del r, okay, d phi by dr, so dr is cancelled, so d phi. So this is phi evaluated at Q minus phi evaluated at P. What does it mean? What does it mean? It means the value of phi at this final point Q and phi P is the value of that function phi at this point P. So it is only depending on the initial point and the final point. It is not depending on the intermediate points, hundreds and thousands of intermediate points. It means if I choose a path like this, then also this integral value will be same, because it is only depending on the initial and final point. If I choose another path like this, it will also not change this value of this integration. Whatever path you choose, it will not change the value of this integration, because for this conservative field we have we have proved that it is only depending on the initial point and the final point. So that is why for a conservative field the line integral is independent of path, independent of path chosen to move from one point, chosen to move from the initial to final point. Now one thing you see, as I told you, for a conservative field, for any vector, let's say A, this is conservative in nature, conservative field. What is the definition of conservative field? How to check? If I give you a vector function, how to check whether it is conservative? So first of all, it can be written as the gradient of some scalar function. Now if you just take the curl of this vector function, what do you get? You get curl of grad phi. And what is the meaning of this? Curl of gradient. Curl of gradient is 0. Curl of gradient of a scalar function is 0. And that is why the best way to check whether any given vector field or vector function is conservative or not, to take the cross product, to take the curl. If the curl come out to be 0, then that vector will be conservative in nature, otherwise not. One example on this regard, this came in CSIR-NET June 2014. So I hope you understood the basic concept of line integral. Let's consider some problem now. If A, this is a vector given to you, C is the circle of unit radius, that is okay, in the plane defined by z equals to 1 with the center on the z axis, then the value of this integral, closed integral c a dot dl. Why this closed sign? Because we are considering a circle. Circle is a closed structure, right? That is why this closed integral is shown, and c is the name of the curve. Can you solve this problem? If I consider the situation, let's say this is x-axis, this is y-axis, and this is z-axis. C is the circle of unit radius in the plane defined by z equals to 1. So this is z is equals to 0, and let's say this is z equals to 1. Your circle is situated at z equals to 1 and with the center on the z-axis. Means the circle is like this. Okay, it has unit radius. This is 1 unit, and this curve is termed to be C. So you have to find out this closed integration e dot d. Okay, another thing I think I forgot to mention, that line integral of a conservative. Okay, look, if this vector A is conservative, then the line integral over some closed curve will always be 0. Okay, this will happen because of this vector field A is conservative in nature. Okay, so let's evaluate this. So first of all, let's check whether this function is conservative or not. So to do that, we have to calculate curl of A. What is curl of A? Can you calculate curl of A? Curl of A, we can write it as I cap, j cap, k cap, del del x, del del y, del del z. A vector yz, zx and xy. So if you calculate this curl, what do you get? Okay, this is, we are getting x minus x plus j cap y minus y, k cap z minus z. So this is coming out to be 0. As since the curl is 0, we can say that A is a conservative field. A is a conservative field, and hence we can say that the closed line integral A dot dl or dr will also be 0. So option D is the correct option for this question. Simple thing, no issue. I am now giving you another problem, and by that problem we'll be able to understand this line integral pretty well. Okay, so the problem is like this, that you have to evaluate. Let me just write the problem, then we'll discuss the solution. Simple problem, but essential to understand the line integral efficiently. Okay, so the problem is like this. Evaluate this line integral f dot dr, where your f is given to be x square I cap plus xy j cap, and c is the boundary of the square in the plane z equals to 0 and bounded by the lines. What are the lines? X is equals to 0, y is equals to 0, x equals to a, and y is equals to a. So this one you need to evaluate. How will you do that? So this is first of all a square, right? Square, we are considering this is the square, and we do not know. Okay, let's say this is the origin, this point is the origin, and this is x-axis. Let's say this is x-axis and this is your y-axis. For our convenience, we have denoted the x-axis and y-axis, and as this is the plane z equals to 0, z equals to 0 means xy plane. On xy plane at each and every point z equals to 0, so we have, that is why we have taken xy plane, right? Bounded by the curve x equals to 0. Which one is the x equals to 0? This one is x equals to 0, this line, right? This line is nothing but x equals to 0. On each and every point of this line x will be equals to 0. Y is equals to 0. Where y equals to 0? Obviously this is your y is equals to 0. At this point, each and every point, whatever point you consider, y will be equals to 0. X is equals to a. X equals to a will be this. If I consider, let's say OA BC, this is the square. If I consider that the side length is a, then obviously this line is x is equals to a, and this BC, this line is y equals to a, because at each and every point here you will get y equals to a. So these are the 4 lines along which you have to find out the line integral. So you see, it is taken in the anti-clockwise direction. Okay, always take the closed curve C to be in the anti-clockwise direction. So you are evaluating the line integral along this path OA, AB, BC, CO, right? So line integral along the closed curve f dot dr, if I just simply write it, how will you write it? F dot dr, first of all along the path OA, then we'll add this to the line integral along the path AB, then we will add the line integral along the path BC, and then CO. So these 4 line integral you have to calculate to get the line integral of f dot d along this closed path. Here C is the whole square path, okay, the perimeter. Now what you require? We require f dot dr. F is already given, this one. We require dr. So what will be dr here? So it is effectively 2-dimensional case, right? It is varying in the xy plane. So as I already told you, it will be dx I cap plus dy j cap. So if this is dr, then what will be the value of f dot dr? F dot dr will be, that take the dot product, x square dx plus xy dy. Now let us calculate the line integral along each path. First of all, we will consider the line integral on OA, right? Or simply you just write OA. So on the path OA, what we can write? On OA, what we have? We have y equals to 0. So if y equals to 0, then what we have? Only x square dx you have. F dot dr is x square dx, because the second term is 0, and that is why the integral on OA f dot dr, it is nothing but integration of x square dx. Here limit of x you have to put. What is the limit of x? 0 to a. 0 to a. So this is x cube by 3. So this is a cube by 3. Okay. Let's go for AB. For AB, what we have? X equals to a. Right? X equals to a. So what will be the value of f dot dr? A square, and here x is not changing, so dx is equals to 0, right? So the first term is vanishing and x equals to a, so this is nothing but ay dy. Here dx is also equals to 0, and here dy is 0. So along the path AB, what is your f dot dr? It is nothing but a times y to dy. Y is varying from 0 to a, right? So this is y square by 2, so a square by 2, this is also a cube by 2. So I think you can easily calculate now the line integral from b to c and from c to a. So let's calculate for b to c. So along the path BC, what we have? Along path BC, we have y equals to a, and you see the value of y is constant. So y equals to a and dy is equals to 0. So what is f dot dr? Only the first term will remain, x square dx. Okay. And hence the line integral f dot dr along BC, right? Yes, BC, it becomes integration x square dx, and you see x is varying from a to 0, right? Here at point B x equals to a, at point C x equals to 0. So that is why the limit is a to 0, and this will be x cube by 3, limit a to 0. So a minus sign will come, minus a cube by 3. BC is done. Let's go for CO. On this line, what we have? X equals to 0, dx is equals to 0, x equals to 0, dx is also equals to 0, and f dot dr equals to x equals to 0 means in both the term x is there, so this term will basically 0, and obviously CO f dot dr is also 0, right? Now if you want to get this whole line integral along the whole path, closed path, entire path f dot dr, then you have to add each of these integrals. So out of these 4 integrals, the last integral is 0, and the first two integrals are a cube by 3 and a cube by 2. Just add them up. So the first integral is a cube by 2, second integral, sorry, a cube by 3, second integral a cube by 2, third integral minus a cube by 3, fourth integral 0. So a cube by 3 is getting cancelled, so only a cube by 2 remaining. So this is the answer. So I hope you have understood this problem. It's a very interesting problem. Once you understand this problem, then I think your concept on line integral is also clear. Let's move on to this problem. This problem is a simple problem. Look at this problem. The line integral a to b f dot dl, where f is given by this along the semicircular path as shown in the figure. Here this is a semicircular path, and as you can see, the line integral is to be evaluated from a to b, and you can see the direction. It is in the clockwise direction. If it were anti-clockwise, then b to a. Okay. So how can you solve this particular problem? Look, x by root over x square plus y square plus y by root over x square plus y square. Now if you look at this geometry, Cartesian, instead of using Cartesian coordinate, if you use polar coordinate, then that will be suitable for us. Okay, these expressions can be reduced, and from this minus 1 0 to plus 1 0, we can say that this radius of this half circle is nothing but 1. Okay, this r is equals to 1. So we are dealing this problem in Cartesian, let's say polar coordinate. In polar coordinate, what do you say? What do you take? We take, first of all, let's write what we have to do. We have to do a to b f dot dr. So this is nothing but point A is minus 1 0, so we have to go to plus 1 0 along the vector function along the curve of the semicircle. So x dx by root over x square plus y square plus y dy by root over x square plus y square. This one you have to evaluate, right? Now we are using polar coordinate, plane polar actually. Look, when you are considering in 2 dimension, it is plane polar. When you are considering the 3 dimension, that is spherical polar. So using plane polar coordinates, we can write x is equals to r cos theta, but as you can see here r equals to 1, so we are simply writing it as cos theta. So dx is equals to how much? We need dx here, as you can see. Dx will be cos theta, so minus sin theta d theta. What you require? You require x dx. So let's calculate x dx. X dx is nothing but x equals to cos theta, so minus cos theta sin theta d theta. On the other hand, we have y equals to r sin theta, r is equals to 1, so it becomes sin theta, and that is why dy is nothing but cos theta d theta, and y dy becomes y is equals to sin theta cos theta d theta. If x is equals to cos theta, y is equals to sin theta, then we can write x square plus y square is nothing but cos square theta plus sin square theta, that is 1. Okay, so obviously root over x square plus y square, that is also equals to 1, and therefore the integral a to b f dot dl becomes, you see, what will be the limit from x y coordinate to r theta coordinate we have converted. So let's calculate it. Let's calculate this thing. So previously, what was the limit of x? The limit of x was minus 1 to plus 1. Y is 0. The final initial y is 0. R 0. Sorry. What is the value of theta? For if you consider this one, x is equals to minus 1. So what, for what value of theta? Cos theta is minus 1, that is pi. And for 1 it is 0. So it is nothing but pi to 0. X dx is minus cos theta sin theta d theta plus y dy is sin theta cos theta, d theta we are taking common. So we have to integrate this from pi to 0, and whatever be the integration result, that will be the answer. But you see these two terms are cancelling, so this is 0. So the whole integral becomes 0. Option B is evaluated to be the correct answer. Okay. So I think this is enough for line integral. Next we are going to move to surface integral. Surface integral is also very interesting thing and easy as compared to the line integral. Okay. So let's talk about surface integration of vectors. Surface integration of vectors. So obviously previously we are defining the line integral over some curve or line. For surface integration we will consider a surface. Obviously the surface integral will be defined over a surface. So initially previously what was there? We had a curve, a vector function. Here also a surface will be there, and for usual region there will be a vector function. So you are evaluating the surface integral of this vector on this surface. Okay, this is the main idea. So let's write. Now surface can be of two types, right? You have seen different kinds of surface. Only different types of surfaces include open surface and closed surface. Closed and open surface, you can see. Closed surface is that surface which contains some volume, like a sphere. An open surface is that surface which does not contain any volume, only area. Like if you consider a rectangular plate, very thin rectangular plate, that is only containing the area, not containing any volume. So that is the open surface. So the integration of a vector on an open or closed surface is known as surface integration of vectors. To make you understand it more clearly, you can see this figure. This is a sphere. It contains some volume, so that is why it is a closed surface. This is simply a plate, does not contain any volume, that is why this is an open surface. Okay, thin plate. Understood the definition? Now let's say an infinitesimal area we are considering here, that is ds. The way we define line integral, the surface integral is defined in a very similar way. For line integral we took the tangent. For surface integral we have to consider the direction of the area vector n cap. So let A be a vector function and S be the given surface. Then we define the surface integral of a vector function A over the surface S is defined as the integral component of A along the normal to the surface. Okay. Mathematically, if I consider the component of A along the normal, so obviously, as I told you already, it is a dot product of that vector and the unit vector along that normal direction. So A dot n cap. What is n cap? N cap is the unit vector on this infinitesimal area ds. ds is some infinitesimal area. So n cap is nothing but the unit vector normal to ds. Okay. So what is the component of this surface integral? Ultimately, how do you define surface integral of A? If you consider over this whole surface, previously we consider only ds, no? So if you want to consider over the whole surface S, then we have to take the sum over all such infinitesimal area. Now this is a continuous thing, so it can be converted into a surface integral, into an integration. So A dot n cap ds. Right. Now two integrations, because if you, there are two dimensions involved, that is why two integrations are there. If you go to volume integral, there will be three integrations. On this regard, let's talk about the volume integral. The volume integral is pretty simple because volume is a scalar quantity, so it is very easier to handle than the other two cases. Volume integral of vectors. Volume integration of vectors. So volume integral of a vector field A within the volume V, what's happening, is given as, we simply write it, triple integration, volume integration is carried out over the volume V, vector A dV. You can imagine that this is the vector, this is the volume, and dV is the infinitesimal volume. So you can imagine it in this way. The way you imagined ds, some infinitesimal area, this is your infinitesimal volume dV, and the whole volume is V, and the volume integral is A dV. Now there are two very important theorems, divergence theorem and Stokes theorem, relating to this open surfaces and closed surfaces, and this divergence and Stokes theorem will help you to convert from line integral to surface integral to volume integral in this way. So let's talk about those two theorems. Those theorems are very important, vector related theorems. Most of the question from vectors previously came from this particular topic. Two theorems. One is the divergence theorem. Another one is the Stokes theorem. You have to remember the mathematical expression for these two theorems. क्या हो रहा है? Okay, first of all, let's talk about the applicability. Divergence theorem is applicable only for closed surface. This is applicable only for closed surfaces. What does it mean? You can apply it to spheres, let's say cylinder. You cannot apply it to some thin disk or plate. On the other hand, Stokes theorem, it is applicable only for open surface. Open surfaces like this. This is an open surface, it doesn't have any volume. Open surface is bounded by some curve. You see, this is the curve which is bounding the open surface. So the Stokes theorem is applicable for open surface. Now what is the purpose of introducing divergence theorem? Basically this theorem, what it does? It basically converts surface integral into volume integral. And the vice versa is also possible, means from volume integral you can come back to surface integral. So you can simply write surface integral to volume integral and vice versa. And what about this Stokes theorem? This theorem, it basically converts surface integral into line integral. Surface integral is common in both. Surface integral into line integral and vice versa, means from line integral you can come back to surface integral. Let's talk about the basic statement in these two theorems, then we'll go for the mathematical form. So what is divergence theorem? Divergence theorem, it obviously contains some volume, so V will come here into picture. So if V is the volume will be bounded by surface, okay now, for a closed surface, and for open surface the area will be bounded by some curve, a line. So if V is the volume bounded by a closed surface, let's say S, and A is the vector function. A is the vector function of position, function of R, with continuous derivatives. Then there is no discontinuity in the derivatives. You take different derivatives, then there will be no discontinuity. Then we write the mathematical form of divergence theorem as, look, when you consider a closed surface, you see the surface of this sphere, it is closed, not open. So that is why we give this symbol of closed. We have already introduced it. Closed integral over the surface S A dot ds. So this is your surface integral. So surface integral we can convert it into volume integral. Okay, and this surface integral has all the form, other form. ds is what? ds is nothing but, if you consider the vector ds, it is nothing but the magnitude of ds and the direction n cap. So that is why sometimes we write a dot n cap ds. This is equals to the volume integral. Volume integral here will be v, and it will be divergence of a dv. So it basically converts surface integral into a volume integral. On the other hand, if you consider this open surface S, so how many surfaces it will have? An open surface will have two ends, like above, below. So if S is an open two-sided, one above, another below, two-sided surface. Look, here volume was bounded by closed surface. Now surface will be bounded by some line. Surface bounded by a closed, you see this line is closed, non-intersecting curve. Let's call this curve to be C. So surface is S and the curve which is bounding that is C. So you can consider this is S and the curve bounding it is denoted by C. If S is an open two-sided surface bounded by a closed non-intersecting curve C, and A is vector function of position with continuous derivatives. So you can see the languages are very similar. Then mathematical form we can write. What do you have to do? Surface integral into line integral, or line integral into surface integral. So here the mathematical form is, here also closed, the curve name is C, A dot dr, this is line integral, it will convert into surface integral. Surface integral, two integration sign will be there, and here you are not giving the close because surface is not closed here. For a closed surface the surface is closed, but for an open surface the surface is not closed. So that is why no closed symbol is given here. Curl of a dot n cap ds, or you can simply write it in this way, curl of a dot vector ds. And as you can see, C is traversed in the anti-clockwise direction. This is the positive direction, where C is traversed in the counterclockwise or in the positive direction, in the positive or counterclockwise direction. So I think you have now pretty much understood these two theorems, and there is a high chance that you will get some question from these two theorems. Let's try some problem. The first problem is this on your screen. If a vector function A is equals to xy x cap plus x square y cap, then what is the value of this line integral A dot dl over the path shown? So here on this path you can see the x value is varying from 1 by root 3 to 2 by root 3, and the corresponding y values are varying from 1 to 3. So A dot dl you have to find out. What will be our first job? Our first job will be to check whether this is conservative or not. If it is conservative, we can simply say it is 0. So let's check whether it is conservative or not. Okay. So to check conservative, whether it is conservative or not, we have to take the curl. So let's say x cap, y cap, z cap, del del x, del del y, del del z. What are the x, y, z components? X component is xy, z, y component is x square, and z component is 0. So what you get? X cap, this is 0, minus y cap, this is also 0, plus z cap, 2x minus x. So this is nothing but x z cap. So curl of A is not 0. So we cannot say that A is conservative. So we have to calculate. We have to calculate A dot dl. A dot dl. We can use the Stokes theorem. Okay. So we can write the line integral in terms of the surface integral by considering curl of A dot ds. Okay, over this surface. This is the surface. What about ds? Ds, you see, this is on the xy plane. So ds is nothing but this area. What is that? Along this side, this is dx, this is dy, and if you take in a counterclockwise sense, what will be the direction? It will be k cap, right? If you rotate it along this, it is coming out this. So ds is nothing but dx dy. What will be the direction? Z cap. Because when you consider the direction of area, it is perpendicular to that. So if you are considering the element in the xy plane, obviously the perpendicular direction will be z cap direction. That is why we have written dx dy z cap. So this becomes integration curl of A dot ds. So here x dx dy. What are the limits of x and y? X goes from 1 by root 3 to 2 by root 3, y goes from 1 to 3. So let's directly put that x going from 1 by root 3 to 2 by root 3. On the other hand, y going from 1 to 3. So dy we can calculate. Dy is y, 3 minus 1 is 2. Okay. And x ds is x square by 2. So 1 by 2 we are taking common. So x square by 2. So 1 by 2 we have taken outside. X square means square of this thing. So 4 by 3 minus square of this thing 1 by 3, and from this integral of dy we are getting 3 minus 1 is 2. So this is nothing but 1. So this value of this integral over this path on is 1. Option B is coming out to be correct. Clear? I am giving you a similar problem as homework. You can try it at home. The line integral, similar problem, very similar. The line integral A dot dl over a vector field, A value is given to you, where r square is equals to x square plus y square is taken around a square of the side of unit length centered at x naught y naught with x naught greater than half and y naught greater than half. If the value of the integral is L, then what will be the correct option among this? Right. Line integral you have to find out. Basically, you have to find out A dot dr or dl, whatever you write, over this curve C. Curve C is this. As you can see, it is in the clockwise direction. Anyways, so on this curve, we have to find out this line integral. And as you can see, this is closed curve, right? So what will be your first check? Your first check will be whether this field is conservative or not. If it is conservative, you can directly say it is 0 and independent or anything. So for this, you will see that the curl will come out to be 0. So L will be equals to 0 and it will be independent of x naught y naught. So option 3 will be correct answer. Take this as homework. Just you will evaluate the curl of this function, curl of A, and this will give you the result 0. So option C, option 3 will come out to be the correct option. Okay, now let's move on to this problem. This is the last problem and we'll wrap up the session here. The value of f dot dr, where f is equals to this, you can see f is nothing but y by x square plus y square I cap minus x by x square plus y square j cap. So we have already done this similar kind of problem before also, today itself. Traversed counterclockwise. So by looking at this x square plus y square and circle, it will be better idea. It will be a better idea to use plane polar coordinate, right? Okay. So when we do not know in which dimension we need to carry, we can generally take it 3 dimension. Okay. So dr, what will be dr? Dx x cap or I cap plus dy j cap plus dz k cap. And as you can see, when we will take the dot product of f and dr, obviously this k cap will vanish. So it is finally coming out in 2 dimension. So close integration f dot dr you have to find out along this circle path, x square plus y square equals to 1, traversing counter clockwise. So it is a circle on the xy plane with radius 1. So first of all, f dot dr, if you calculate, what will be its value? It is nothing but, you see, I cap and I cap, y dx is coming, y dx divided by x square plus y square, and here minus x dy divided by x square plus y square. This is coming, and x square plus y square is given to be 1. So it is nothing but y dx minus x dy. This one ultimately you have to find out. Why you could write? Because x square plus y square equals to 1. So it will be a better idea if you go with the plane polar coordinate. So we can put x is equals to, and r is equals to 1. So r cos theta. So we are not writing r equals to 1, you know, x equals to cos theta, y equals to r sin theta, means y equals to sin theta. So it is a kind of similar problem which we have done earlier. Dx will be minus sin theta d theta, and dy will be cos theta d theta, right? And hence your f dot dr will become, again you can use this technique to change the value of these limits. So if you want to change the value of this limit from x, let's say x to theta, okay, then you can do that. Or you can simply write, if you do not do this, you can simply you can write that the value will be 0 to 2 pi. Theta is varying from 0 to 2 pi. Ultimately you are representing theta, na? In plane polar coordinate, the value of theta varies from 0 to 2 pi, right? So 0 to 2 pi, y dx, y is sin theta, dx is minus sin theta d theta, minus cos theta d theta, and we know the range of theta to be 0 to 2 pi. So minus sin square theta minus is let's say taken outside, 0 to 2 pi sin square theta, and plus cos square theta. You can write it in this way, d theta. This is 1. So minus theta varying from 0 to 2 pi. So minus 2 pi it comes. It is matching with option 4. Option 4 is the correct option for this question. Okay, so in this lecture we have covered the line integral, surface integral and volume integral in detail with some numerical, and we also discussed some vector related theorem, the most important, divergence theorem and Stokes theorem. And I hope this lecture will be very beneficial for all of you in various examinations like CSIR-NET, GATE, JEST, TIFR, BRC. Everywhere you go, this thing will be equally helpful. Okay. So we have covered this much, and from the next class we will start quantum mechanics. Okay, so you can consider it in this way, that the first 3 days of the week, Monday, Tuesday, Wednesday, will be going for MMP, mathematical methods of physics, and in the next 3 days maybe quantum mechanics, means Thursday, Friday, Saturday, and every day we'll try to take the class at 8 AM. So try to attend the class live. These classes may not be live for a long time, so it is asked to attend the classes live. That will be useful for you if you attend the classes live, and all these classes will be uploaded in the app also. You can also get all the lectures and the PDFs of this class notes in the app itself. You can get the app by scanning this QR code, and by also visiting this website you can get the app, or you can simply download this app from the Play Store. And you can join the Telegram channel by using this Telegram channel ID, and you can also join the WhatsApp group. The WhatsApp group is given in the description. So thank you very much guys for watching this session. If you are new to this channel, please subscribe the channel and don't forget to press the bell icon. Finally, thanks for watching. Hello, 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 hello. Am I audible? Hello, 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 hello. Okay guys, so let us start, if everything is all right. So we will start, we have started with mathematical methods. You know, there are total 9 units in your CSIR-NET Physical Sciences syllabus, and you always start with mathematical methods, because there are some techniques in mathematical methods which are very necessary to understand if you want to cover other subjects like quantum mechanics, classical mechanics, whatever subjects you cover. You first need the basis. Okay, mathematical methods gives you. So in this course we have already uploaded 4 lectures on vector analysis. Okay, So we have started with mathematical physics, and in the mathematical physics we have uploaded the lectures for dimensional analysis, one lecture for dimensional analysis, then lecture 2 to lecture 4 vector analysis. These are very simple topic, easy topics, you can easily understand. And today we will be discussing lecture 5 vector analysis part 1. This is the last part of vector. So in total 4 lectures we are covering the vector part. Now before I go, let me tell you what you will find in the course folder. Okay, we have uploaded or revamped actually the course folder. So we have added this short notes section separately. So as we proceed with the course, as we cover different subjects, we will keep on uploading these short notes. Okay. So for the time being, we have uploaded the short notes for mathematical methods, because we will be covering mathematical methods. And second thing I have added there, textbook, standard textbook, standard textbooks. So these all you will get if you go to the course folder, or the course you have purchased. In the course folder you will get these folders. So in the standard textbook, you know, for each subject you need at least 1 or 2 books. So keeping that in mind, for each and every subject starting from mathematical methods to particle physics, for each subject I have added 1 book or 2 books. Okay, so that you can also download. And guys, everything is all right now? Tell me. And if you have any question, you can ask me. And this is a live class, and after this live class, this recording of this video and as well as the PDFs will be uploaded into your course folder. So if you do not want to miss anything, you will just check the course folder. Whatever things we will do, everything will be uploaded in the course folder, which you can see anytime. Okay, these are the 2 things. And thirdly, we are starting from mathematical physics. In the mathematical physics, as I have already told you, 4 lectures have been already uploaded. So if you are watching this lecture for the first time, you can watch the previous lectures. Lecture 1 give you dimensional analysis, lecture 2 to 4, there are 3 videos on vector analysis, and today we will be taking the lecture 5, that will be the vector part 4. Okay, and what I was thinking of telling you. Okay, fourth one, which will talk about assignments. Assignments, there is a separate folder for assignment. So what you will be doing, let's say we are now in preparation the assignments for dimension analysis. So let's say mathematical method, so assignment number 1.1. okay, this will be your assignment on dimension analysis. Then we will go for 1.2. 1 means this is the subject, first subject, mathematical physics. So this is the number of assignment, dimension analysis. Then we will give you assignment on vector, then matrices, and so on. For classical mechanics, it will start from like 2.1, 2.2, 2.3, then so on, 9.1, 9.2, 9.3, and in this way assignments will be uploaded. Okay, now see assignments. Let's say there will be 10 question or 15 question or 20 question depending on the topic which we are discussing. Let's say for the time being, I am just giving an example, 20 questions are there in the assignment. So out of those 20 questions, mostly we will try to cover those questions in the lecture. Okay, we will incorporate those questions in the lecture. Let's say I give you the solution, detailed solution while taking the lecture. Let's say 15 questions, and 5 questions will be there which you have to try by yourself. I am just giving you, it may be 10 plus 10 also, 10 question I give you in the lecture, 10 plus and another 10 in the assignment. Although I will upload the PDF solutions, but you will try, and in the assignment there will be some answer key also. Okay, so in this way we will proceed as we keep on completing the topics, the assignments, related assignments will keep on getting uploaded in the course folder. You will get everything in the course folder. Okay, any doubts, guys? And if you also have any suggestion, you can also give me. If things can be better in any way, if you think any point, you can suggest me. I will definitely try to incorporate. And other than that, okay, another component which I have not added, but will try to take 4 tests a month, right? 4 tests a month, like in every week, preferably on Sunday, maybe some 10 a.m. you can give a test. It will the number of questions in the Sunday test will depend, like whatever portion we cover. If you cover a small portion, then number of questions will be less, let's say 10 or 15, 20, 30, depending on how much we cover in the previous week. Okay, so this is about this course folder and all. Now let's start with our actual discussion. Today is like an introductory class, and in the first 4 lecture we have covered significant portion of the vector analysis. I have already uploaded the video PDFs, you can watch it. And last portion of this vector analysis left. In that portion we will be talking about the linear dependency and linear independency. Okay, let's start. Any question, guys? You can ask. And let me tell you another thing about the doubt clearing. You can ask during the live classes, or you can WhatsApp in the group, or you can personally DM me also anytime. Okay, whenever I will be able to reply, I will reply. Okay, if you don't have any question, let's start with this linear dependency of vectors. So you must have seen 1 or 2 questions based on this topic, linear dependency and linear independency. So what do we understand by this? By simple term, whether some vectors are linearly dependent or independent, if you can express one vector in terms of other vectors, then they are linearly dependent vectors. If you cannot, then that is linearly independent. Okay, linearly independent set of vectors means you cannot express one vector in terms of the others. So let's say if you have 3 vectors, okay, 3 vectors, we have u, v and w. So these are 3 vectors, so they each vector will have 3 components, x, y, z components. So these 3 vectors, if you are given, they will be linearly independent. Under what condition they will be linearly independent? Linearly independent if they satisfy this criteria. Let's say some constant alpha 1 times u plus alpha 2 times v plus alpha 3 times w, if this is 0. Okay, where this alpha 1, alpha 2, alpha 3 are all 0. So if you see, if this condition gets satisfied, that if you take alpha 1 u, alpha 2 v, alpha 3 w, if you want to make it 0, there should be only one possibility, that you choose alpha 1 equals to 0, alpha 2 equals to 0 and alpha 3 equals to 0. Then u, v and w will be called linearly independent vectors. And when you understand that these vectors are linearly independent vectors, those vectors will form the basis. Basis means what? Like if you take the case of your Cartesian coordinates, I cap, j cap, k cap, these 3 vectors are linearly independent vectors. You cannot express I in terms of j or k, you cannot express j in terms of I cap or k cap, or you cannot express k cap in terms of I cap and j cap. So I cap, j cap and k cap, they are linearly independent vectors, and they are said to span the space. What is the meaning of span the space? Spanning the space means with the help of those vectors you can express any vectors. Okay, so this is the theoretical perspective that you need to have alpha 1, alpha 2, alpha 3 all to be 0. Okay. Now write another line, and they form the basis of, this is the real space, real three-dimensional space. What is the meaning? Form the basis, meaning that any vector in R3 space can be written as the linear combination of U, V and W respectively. Okay. So this part is okay. If someone asks you what is the condition of linear dependent or linear independent, you can state this. Now the question is how to check. This is for your exam purpose. In your examination you must have seen many questions. How to check whether the set of vectors are linearly independent or dependent. Okay, how can you check? So there is a simple technique to check this. You see, what you have to do, you have to find out the scalar triple product. The scalar triple product. Scalar triple product is formed by three vectors, right? Scalar triple product. What is the value of scalar triple product? We have already defined in the previous lectures of vectors. Scalar triple products of three vectors, let's say u, v and w you have, then the scalar triple product will be u dot v cross w, right? This is your scalar triple product, and you know the value of this. How to get the value? It is the determinant. What you have to do, you have to write the components of u. So if you have u, what are the components of u? Is u1, u2, u3, isn't it? So it is like u1 x cap or I cap plus u2 y cap plus u3 z cap, right? Similarly, you can also write v is equals to v1 x cap, v2 v is equals to, you can write, I am just writing in this way, v1 v2 v3, okay, and w w1 w2 w3. These are components. So you can express it in terms of this also. So u dot v cross w will be your, you just need to write the components row wise, u1 u2 u3 sorry, v1 v2 v3, and for w this is w1 w2 w3. So this determinant is formed if you find it not equals to 0. Remember, if it is not equals to 0, then we call it, this is the criteria for linearly independent vectors. So if the determinant is found to be not equals to 0, it is linearly independent. If it is 0, then linearly dependent vectors. Understood? Now there are two very important things: orthogonal vectors and orthonormal vectors. Let us talk about them. Look, these concepts are very simple, but you need to have the understanding of the fine difference between different terms like orthogonal vectors, orthonormal vectors. They are not same. There is a slight difference between them. So let's talk about orthogonal vectors. If I talk about in simple terms, what is orthogonal vector? What are orthogonal vectors actually? So if the dot product is 0, like normal vector you have a dot b is equals to 0, then we can call them orthogonal vectors. So let's just write the definition. We say that two vectors, numeric 2 is looking odd. Two vectors are orthogonal if they are perpendicular to each other. Now if two vectors are perpendicular to each other, their dot product will be 0. You see that we say that two vectors are orthogonal if they are perpendicular to each other. That is, how do you determine? The dot product of the two vectors is 0. So whenever you will be asked whether the given set of vectors are orthogonal or not, you will just take the dot product. This is the first definition. Now let's talk about orthonormal vectors. Orthonormal vectors. So we can understand it by looking at the name carefully. Orthonormal. So it is like combination of orthogonal plus normalized. So for orthonormal vectors, the conditions will be orthogonal, that is the previous condition, plus each vector will be normalized to unity. Normalized to unity, you understood? So let's talk about, we say that again, a set of vectors. We'll do some example, don't worry, you will understand it. Let's say v1, v2 and so on. Let's say n number of vectors are there. So in your examination they may give you 2 vectors or a set of 3 vectors. Now when we talk about multiple vectors, more than 3, 4, 5, so we use this term mutually orthogonal. Mutually orthogonal. So it is like एक दूसरे के साथ orthogonal, mutually orthogonal. We say that a set of vectors are mutually orthogonal if every pair of vectors is orthogonal. Okay. In common terms, if you can see v1, v2, v3 and so on. So any vector you can denote by vi. Any pair will be vi dot vj. Let's say if you choose I equals to 1, j equals to 2, then it will be v1 and v2, dot product between v1 and v2. If you take v2 and v3, then it will be I is equals to 2, j equals to 3. So vi dot vj, this is for general dot product for any pair. It should be 0 for all I not equals to j. So it is like, it is saying that you cannot take the dot product of vi, v1 and v1, v2 or v2. They should be different. Okay. So okay, orthonormal. This is not orthonormal now. So this is under orthogonal vectors only. Sorry for this. It is like another part of it. This is for 2 vectors This is for more than 2 vectors. So we'll come to the orthonormal vectors after this. Let's take an example. Let's say we are given this set of vectors. Let's say 1 0 minus 1. This is one vector. This is v1. 1 root 2 1. This is, let's say, v2, and 1 minus root 2 1. Can we check whether they are mutually orthogonal or not? Are they mutually orthogonal? Please do and let me know. Are they mutually orthogonal? Like if you take the dot product 1 0 minus 1, you can write it in terms of vector, then you can check dot product 1 root 2 1. Dot product means 1 into 1, 0 into root 2, minus 1 into 1, and plus. So it is 1 plus 0 minus 1. So this is 0. If you take the dot product between 1 0 minus 1 and 1 minus root 2 1, again you find it 1 0 minus 1, that is 0, and if you take the dot product 1 root 2 1 dot 1 minus root 2 1, then it is 1 minus 2 plus 1. So again it is 0. So you see, you take any pair and you take the dot product, it will give you 0. It means these vectors, the set of vectors, this and this is mutually orthogonal. Understood? When we talk about only orthogonal, means it is between two vectors. Mutually orthogonal means you have to consider set of vectors and each pair of vectors will be mutually orthogonal separately. Now, if this is done, we can go for orthonormal vectors. So let's go for the definition. A set of vectors S is orthonormal. Set of vectors S means, in this way you can consider v1, v2, v3 and so on. If every vector in S has a magnitude of 1, so this is normalized, magnitudes to normalized to unity, and the set of vectors are mutually orthogonal. So let us check the previous example which we considered. Okay, so let's say we have v1. Sorry guys. 1 0 minus 1, v2, let's say another vector 1 root 2 1, and V3 what we had 1 minus root 2 plus 1. So the set of vectors are mutually orthogonal, which you have already seen. Okay, now let's check whether they are normalized or not. So obviously they are not normalized. If you take square root of 1 square plus 0 square minus 1 square, then that is not 1. V2 is also not equals to 1. You know how to find out the magnitude. Let's say if you have a vector like this, a vector ax I cap plus ay j cap plus az k cap. How do you find out the magnitude? Magnitude is found out by taking the square root of the component square, summation of component square, ax square, ay square, az square. This is the way you find out the magnitude of a vector. Same goes for here. If you consider this v1, v2 or v3, none of them are having a magnitude of 1. But what you can do, let's say I am defining another set of vectors. Let's say u1 is v1 by modulus of v1. What do you expect? It's a unit vector along v1 direction, so it must be 1, and you will see it will become 1. So what is the modulus of v1? Root over 1 square plus 1 square, so root over 2. So it is 1 upon root 2, 1 0 minus 1. So what you get? 1 upon root 2, 0 minus 1 upon root 2. Now if you take the magnitude of u1, obviously you will get 1, right? 1 by root 2 whole square plus 0 square plus minus 1 by root 2 whole square. Now it is giving you 1. So this u1 is normalized. Now u2, it is, let's call it v2. So vector v2 by modulus of v2. Similarly, what you get? You see, what is the magnitude here? Root over 1 square plus root 2 square plus 1 square. So this is 1 root over 4. So 1 by 2 will come here. 1 root 2 1. Okay. 1 by 2, 1 by root 2, 1 by 2. Again, if you calculate the magnitude, it will give you 1. Similarly, it goes for a vector sign missing. V3, vector v3 by modulus of v3. Again, you will get 1 by 2, 1 minus root 2, 1 by 2 minus 1 by root 2, 1 by 2. Again, if you calculate the magnitude, you will get 1. So to check whether the given vectors are orthonormal vectors, you have to consider the magnitude, that should be 1, and they should be mutually orthogonal. These two criteria needs to be fulfilled. Now we can say that the set of vectors v1, what we have written, u1, u2 and u3 करते हैं. u1, u2, u3. are orthonormal, but not v1, v2, v3 are orthonormal. Although they are not although they are orthogonal, but they are not orthonormal. Okay, so I hope you have understood.
hold on a moment. Now, if I say another line, okay, question came. Okay, one line I would like to give, but I don't have space. Anyways, if you have a space, you can write after it. Okay, then we'll go for this problem. An orthogonal set of non-zero vectors is linearly independent. So, if you consider V1, V2 and V3, then they will be linearly independent. So, as I told you, what is the condition for linearly independent? What was the condition? In the first slide, we have talked about it, u dot v cross w. So, if you can check whether these vectors are linearly independent or not, what you have to check? V1 dot V2 cross V3. है ना? V1 dot V2 cross V3. So, what you have to check? 1 0 minus 1, 1 root 2 1, 1 minus root 2 1. So, what we have done? We have just write the components 1 0 minus 1, 1 root 2 1, 1 minus root 2 1 along the rows. Okay. So, if you find out the determinant, what you get? 1, here it is root 2 plus root 2 and 0 minus 1 minus root 2 minus root 2. So, obviously, this is not equals to 0. So, if this is not equals to 0, then we can say V1, V2, V3 are linearly independent. That is why V1, V2, V3 are orthogonal set. An orthogonal set of non-zero vectors is linearly independent. They are not zero vectors. Understood? So, I hope you have clearly understood the condition for linearly independent, linearly dependent, orthogonal, orthonormal and normalized. These are the few things. Now, you can answer any question. Okay, let's take this first question. Identify the correct statement for the following vectors: A is equals to this and B is equals to this. The vectors A, B are linearly independent, linearly dependent, orthogonal, normalized. Tell me which one is correct. Do it quickly. Look, although we will be uploading these videos in the recorded form in the course folder, you should attend these classes live. Then you can learn it in a systematic way. Okay, and if you have any doubt, you can ask. So, you have to check this criteria. Let us try to find out. Firstly, what is given? We are given two vectors. One is, so what are the given vectors? A is given to you
3i plus 2j cap, 3i cap plus 2j cap, and B is given to you I cap plus 2j cap. So first of all, let's check whether they are normalized or not. A, B are normalized. So check modulus of A is root over 3 square plus 2 square. So obviously this is not equals to 1. So A is not normalized. And if you talk about B, so this is root over 1 square plus 2 square. This is also not equals to 1. So A, B are not normalized. So fourth option is incorrect. Orthogonal, you can check. They are not orthogonal. They are not orthogonal actually. If you take the dot product to check orthogonality, dot product is 3 plus 4, 7. That is not equals to 0. So that is A, B are not orthogonal. A and B are not orthogonal. This is the first problem. That is why I am showing you how to do each thing. Now let's check the linearly independent or being dependent. So what you have to do. You have to just, for 2 dimension, what you have to do, you have to just write the components of the vectors row along the row 3, 2, 1, 2, as you can see. So this is 6 minus 2, that is 4. 4 is not equals to 0. If it is not equals to 0, means A and B are linearly independent. So the first option is the correct option. Understood? If this is done, let us move to the next question. Let E1, E2 and E3 vectors are given. Let S is a set of vectors consisting of E1, E2 and E3. Let R3, this is a real space. R3 denote the 3-dimensional real vector space. Which one of the following is correct? You can let me know the answer in the comment section. S is a linearly dependent set, or S is an orthonormal set. S is a basis for R3, or this criteria is getting satisfied. A, B or C or D? Which one is correct? Are you able to do it? Look, this is clearly seen 1 0 0 1 1 0. So this is not normalized to unity. This is also not normalized to unity. This is also although normalized to unity, but overall set S is an orthonormal. So this is incorrect. You can directly eliminate this. Now if you can determine whether it is linearly independent or dependent, then you can eliminate one of these two. So option, because only one option is correct, So the correct option must be from these two, A and C, isn't it? If it is linearly independent, then that will be basis for R3. If it is dependent, then there is no question, option A will be correct. So let us check whether the given set of vectors are linearly independent or not. So what we have to do to check? We have to form the scalar triple product E1 dot E2 cross E3, and you need to just write it all the vectors along the row 1 0 0. So we write it along the row 1 1 0. Let me tell you once again, 1 1 0 means it is I cap plus j cap, and this means I cap plus j cap plus k cap. This is the meaning I cap. Okay, 1 0 0 1 1 0 1 1 1. Let's find it out. 1 into 1 minus 0 minus 0 plus 0. This is 1, which is not equals to 0. It means these three vectors are linearly independent, and they can be a basis for R3. Therefore, the given vectors are linearly independent and hence can form a basis for R3. Fine. Let us move to another question. This topic is small, as we are on our first day, so I have taken small topic. After this session, we will start matrix portion, and you will get all the lectures arranged in a proper way inside the course folder, and this recording will be uploaded just after the class. Now give it a try. This next question: consider the set of vectors, and 4 options are given: the orthonormal, linearly independent, they form basis, or you can write one vector as a linear combination of the other two. Can you tell me which one is correct? Are they orthonormal? Look, they are normalized, right? You consider the magnitude is 1, here the magnitude is 1, here also the magnitude is 1. But are they orthogonal? Orthonormal condition needs to be read by this orthogonal plus normalized. So the second condition, normalized, being satisfied. But are they orthogonal? They are not orthogonal. If you take the dot product, are they orthogonal?
No, they are not orthogonal. So the first option is not correct. Now let's check linearly independent or dependent. So look, the concept is simple. I'm just giving you multiple problems just to make you understand one simple fact that A dot B cross C, this is the way to choose it, way to check it. If you consider this vector is A, this vector is B, and this vector is C, then you can write it in this way: 1 by root 2 1 by root 2 0 0 1 by root 2 1 by root 2 1 by root 2 0 1 by root 2, and if you check this determinant, you will get it not equals to 0. You can do it by yourself. It's a simple thing to check. Actually from here you will get half. Okay, so it will come out to be not equals to 0. So this is linearly independent. This is correct. Now if they are linearly independent, three vectors cannot form a basis. This is incorrect. Yeah, they can form a basis. 1 by root 2 1 0 1 1 0 can be written in a linear combination because they are independent, linearly independent vectors, and no vector can be written in terms of the other two. So this is also incorrect. So option B is the correct option. A is not. You have to find out the correct option, right? So B is the correct option, no? Okay. So one question I am giving you as homework. You can try it at home, and we can discuss the solution in the next class. And I don't think you require any solution for the problem because you have understood. Okay, so let me just summarize it again. What you need: firstly, to check linear dependency, the scalar triple product should be 0 for linearly dependent and non-zero for linearly independent. Secondly, orthogonal vectors. This is today's learning. And mutually orthogonal vectors, when we have more than two vectors, mutually orthogonal vectors. So for a set of vectors, each pair should be mutually orthogonal. Then we learned about orthonormal. So I think now the difference is clear between these terms. Okay, now take this problem as homework. You can do it in few seconds, 30-45 seconds you can do it. V1, V2, V3, which one of the following statement is true for this set of vectors? Orthonormal vectors, orthogonal vectors, linear dependent vector, they can constitute a basis for spanning a 3D real vector space. Okay guys, so this is all for this session. We'll continue our session on the next day. So we have kept the session timing 8 AM. Okay, I will share the session links maybe few minutes before in the WhatsApp group for the timing, and after the live sessions the recording and the PDFs will be uploaded in the course folder. From there you can access it anytime. Okay, any question from you guys? You can ask, otherwise we'll end up the session. Okay, so if you don't have any queries, we are ending the session here.
Thank you very much, guys, for joining this session, and see you soon. See you tomorrow at 8 a.m. again. Till then, bye bye. Take care. And I will try to upload the assignment as soon as possible. It is under preparation. Okay. Chalo. Bye. Hello, guys. Good evening. Good evening to all of you. Welcome to our YouTube live session. In this session, we'll be talking about the coordinate system. Look, these coordinate systems are very basic thing. You must understand this before you start subjects like electromagnetic theory or mathematical physics. So mainly we talk about this Cartesian, spherical polar and cylindrical polar. On another coordinate system is that is plane polar. So today in this session we'll be talking about all of them, and we'll also try to understand what different expressions of gradient, divergence, called Laplacian in different coordinate system. So this one lecture will be very helpful for you if you are preparing for different competitive exams in physics. Okay, so let me just check about all of them, and we'll also try to understand what different expressions. Okay, so I think everything is all right. So let's move out. Okay, so before we start, if you have not installed our application, you can install it from Play Store. You can also scan this QR code and you can get the application. And guys, before I start, let me tell you that this course has been launched, top 100 most important topics for CSIR-NET 2024 Physical Sciences. Here we'll be covering 100 most important topics for your upcoming CSIR-NET exams, and you can get all the details by visiting this website www.physicshub.in. all the links are given in the description. And other than this, you know, all ISRO scientist or engineer SC test series also there. You know, ISRO examination day has been announced. It will be conducted on 18th of April, so you can purchase this test series if you are appearing for that examination. Okay, so without any further ado, let's start today's discussion. So first of all, what you have to do, what we will do, we'll be talking about the Cartesian first, because unless and until you understand the Cartesian, you will not be able to understand the spherical polar and cylindrical polar. So although all of you know, for the sake of completeness, we'll start with Cartesian coordinates. Okay, then we'll just generalize the thing. Cartesian coordinate. So when you talk about the Cartesian coordinate, we deal with three variables. We can say x, y and z. This is the first thing. So in Cartesian coordinate, we take these three axes x, y, z. This is like we are doing it from the very beginning. That is why we are also doing these simple things. It may not be simple for all of you, but you need to understand this first before we move on to spherical polar and cylindrical polar. So here we have the three unit vectors x cap, y cap, z cap. Sometimes you also write it in terms of I cap, j cap or k cap. Now if you want to specify any point in a Cartesian coordinate, you know how we do that. We go along x axis. Okay, let's change the color, that will look good. Then you go along the y axis, then we reach to this point. Okay, let's say this point is P, x, y, z. Okay, this is x, this is y, and this is z. So this is a very basic thing you already know. Let's define a vector r. Then for this Cartesian coordinate, how do you define r? R we define it in this way: x cap plus y cap plus z cap. Now it is very easy to understand the length element in this Cartesian coordinate. But before that, what will be the magnitude of this vector r? Root over x square plus y square plus z square. And you also know that any unit vector along this direction. So this is the vector r which connects origin to a particular point P. And if you want to find out the unit vector along this direction, then what you do? We do vector r by the modulus of r. This modulus of r is sometimes also written like simple r. Okay. Now for all the coordinate system, we will try to understand three things. One is line element. How we consider line element? Then we will consider surface element. Then we will consider the volume element. So in Cartesian, it is very easy to understand. Like, let's say this is one point. Now if I move along this, then we can define the line element, let's say dl. How do you get dl? dl in Cartesian coordinate we define as dx x cap plus dy y cap plus dz z cap. So how you can comprehend this? It is like you are moving small amount along x axis, okay, like this, small amount this dy along y axis and small amount along z axis, and you get to the new point. In Cartesian coordinate, it is very easy to understand this dl. Okay. Now try to understand this very carefully. Whenever we will define this surface integral or volume integral, these things will be very important. So let's consider volume element first, then we will go for surface element. Look, line element and volume element, these two things are easy. Surface integral has some complexity which we will try to understand. So deta is nothing but the product of dx, dy and dz. Okay. So line element is done, volume element is done. Now let's go for the surface element. Surface element, or also we can call area element. First we are covering Cartesian, then we will go for spherical polar and cylindrical polar, and if you guys have any question you can ask me. Okay, I am doing from very scratch so that you understand completely. Now when you talk about area element, area in mathematical physics, you can experience two types of area we generally encounter. One is open surface, another one is closed surface. Open surface and closed surface. What is the difference between an open surface and closed surface? Open surface is that surface which does not include any volume. It may be a simple area like this, a plate. So this is in 2D. It does not contain any volume, no volume, only area. So this is an example of open surface. Okay, simple plane. Now what will be the example of a closed surface? Closed surface may be some sphere which contains volume. Okay, this is a sphere, let's say. So it contains volume. So for both the cases, we will try to define the area element. First of all, let's consider the closed surface. Okay, and we will define the area element. One standard rule you will keep in mind here. Note, line element, volume element, they don't have any direction, they are scalar thing, but this surface this is a vector thing, and what is vector will have its magnitude as well as direction. What is the direction of the vector? Always remember, when we will talk about a direction of any surface element, it will be outward drawn normal. Okay, every time follow this and you will not get confused. Okay, so let's take some closed surface, then we will try to understand how we define different surface element. Look, in Cartesian it will be very easy for you to understand, and if you understand it clearly in Cartesian, it will not be a big deal in understanding the in spherical polar and cylindrical polar. So first of all, we need to consider this coordinate system x, y, z. Now what we are considering? We are considering some cube. Okay, so let's consider a cube like this. Let's say the dimension of this cube is a. ये थोड़ा सा अलग हो गया cube, but let's say this is a, this is a, this is a. So it is cutting x, y, z axis at a. Now can you name this? This is the origin. What is this plane? If I am talking about this plane, what is this plane called? This plane is your x is equals to 0 plane. Okay, and what about this plane? What about this plane? What is this plane? This is your y equals to 0 plane. Okay, and what about this plane? This is your z is equals to 0 plane. Okay, now let's say we want to define some area, and as you remember, I have already told you, area means, direction of area means you have to consider outward drawn normal. So I am considering an area element at this surface. What is this surface? This surface is x is equals to a. Okay, similarly, if you consider this surface is y equals to a, and if you consider this surface, upper surface, that is your z is equals to a. So I hope you can easily understand this. Now what will be the direction? We have to consider outward drawn normal. So we are drawing outward. So this is your x is equals to a plane. If you go along this infinitesimal change is dy. If you go along this infinitesimal change is dz. So what will be this area? This area will be dA, infinitesimal area, so di into dz. Okay, we have written the magnitude. Now if you want to consider the direction, so direction of dA, you see this is positive x axis, so this is x cap. If you consider a symmetrically opposite infinitesimal area like this, so for this the outward drawn normal will be in the negative x direction, in this direction. Okay, so for this the direction is negative of x. So here the area will be, you see the things are remaining same, and if you consider the vector, it will be minus x cap. Understood? So this is we have defined for closed surface. Similarly, you can define the area element in any of the planes. Okay, so this got a little bit messy, so I am drawing a fresh figure for you, then it will be better to understand. X cap, y cap, z cap. Okay. Now let's say I am showing you an infinitesimal area on this plane. Do identify this plane? This is 0, this is A. So this is your Z is equals to A plane, right? So if I draw the outward drawn normal, what will be the direction? This will be the direction Z cap. Okay. So what will be this infinitesimal area? On this we have varying dx, okay, along this dx, along this dy. So this will be dA is equals to dx dy, and if you give the direction, it will be Z cap. And if you consider a symmetrically opposite infinitesimal area here, what will be the outward drawn normal? Outward drawn normal will be along this, along the negative Z cap direction. So what will be this area element? This area element will be dA is equals to dx dy minus Z cap. Okay. So one thing you can notice, whatever plane you consider, the direction is coming from that only. Here we have considered x equals to 0 plane, x equals to A plane. You see the unit vector direction is along x cap. If I consider z equals to 0, this plane is z is equals to 0 plane, right? Z equals to 0 plane or z equals to A plane, the unit vector along Z cap. Similarly, if you consider an area element here, this, what is this plane? This plane is y is equals to A plane, and what is this plane? This is y is equals to 0 plane. So your unit vector direction will be along this, and if you consider an infinitesimal area here, the unit vector direction will be along this. This will be along negative y cap direction, and this is along positive y cap direction. So I hope you have understood. These are all for the closed surface. Okay, closed surface elements. Now let's quickly tell you about open surface. Okay, for open surface, how do we tackle the area? For open surface, there is no volume. Okay, so first of all, we need to draw the coordinate system. Okay, in this way. Try to understand very carefully. These are very fundamental thing. Many of you know, many of you do not know, but after this lecture, you will be able to do it easily. I am giving you an area. This is the open area, open surface area. Look, for open surface area, look, for closed surface area, there is no sign in which direction it is traversed, but for open surface area you must have some sign along which the direction the open surface is traversed. So let's say we are considering this anti-clockwise. Now if I consider an infinitesimal area on this open surface, so here what is varying? Dy. Along this direction what is varying? Dz. So how can you write the area element here? So dA will be the product of dy and dz. What about the direction? In which direction it is being acting? Look at this orientation. So it is like anti-clockwise. So if you rotate something anti-clockwise, in which direction? It will come to along x direction, right? If something is on yz plane, if you rotate, in which direction it will point? It will point along x direction. So that is why the direction is x cap. Let's take another area here. But now I am giving another direction like this, 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 this. This is below this xy plane. This is in clockwise direction. Now if I consider an infinitesimal area here, what is varying along this direction? This is dy. What is varying along this direction? This is dz. And from this you can see it is pointing in the negative x direction. So this infinitesimal area we can write it as dy dz, and the direction will be minus x cap. Okay. So I hope you understood the concept of closed surface and open surface. Let's now quickly tell you about this gradient, divergence, curl and Laplacian in case of Cartesian coordinates. Okay. First of all, gradient. This whole thing will repeat in case of spherical polar and cylindrical polar. Gradient is defined for a scalar. This is the definition of this is a mathematical expression of gradient. Del del x I cap, del del y j cap, del del z k cap times phi. So this is del phi by del x I cap, del phi by del y j cap, del phi by del z k cap. So as you can see, this is a vector quantity. So gradient of a scalar is a vector quantity. Let's talk about divergence in case of Cartesian coordinates. Divergence is defined for a vector. So let's say V is a vector. So divergence of V is equals to del Vx by del x, del Vy by del y, del Vz by del z. As you can see, this is a scalar quantity. So divergence of a vector is a scalar. Third thing is curl. Curl of some vector, let's say that vector is V. You know it. How we write the unit vectors? I cap, j cap, k cap. Then we write the components of this grad operator, del del x, del del y, del del z. Then we write the components of V, Vx, Vy, Vz. So curl of a vector is also a vector quantity. In Cartesian, things are pretty straightforward. Things get little complicated when we move to spherical polar and cylindrical polar. So these four things will always be useful in your electromagnetic theory and all those things. So grad square phi, this is the grad square, this is called Laplacian. Laplacian of a scalar, grad square phi is defined in this way, and as you can see, this is also a scalar quantity. Okay. So this is pretty much about the Cartesian coordinates. Let's quickly move to the spherical polar coordinate. In spherical polar coordinate, what you use instead of x, y, z, we use here r theta phi. So, your Cartesian coordinate is like a reference, and with that reference we will define these coordinates. So, in spherical polar coordinates we can define a vector, let us say A. It will have r component ar, and unit vector along r, plus a theta unit vector along theta, and a phi unit vector along phi. So, it is very easy to understand the unit vector of x cap, y cap, z cap, but what about this unit vector r cap, theta cap and phi cap, in which direction they point? Okay. So, let us consider this coordinate system again. So, in the whole discussion, Cartesian coordinate will be our reference point. This is your x cap, y cap, z cap. So, if you want to define a particular point, let us say P, in a spherical polar coordinate we have to define with these three coordinates r, theta, phi. What is r? R is the distance from the origin to that particular point. This is the origin, let us say. So, r is this distance. What is the theta? Theta is the angle made by this radius vector with the z axis. Okay. So, this is your theta. What about phi? Phi, to get the direction of phi, you have to take the projection on the xy plane. Okay. And this projection of this radius vector, whatever this projection makes the angle with x axis, that is your phi. So, this is the pretty much thing. Okay. So, you can just quickly write what is r. R is the distance from the origin. What about theta? Theta is the angle made by the radius vector or radial vector, you can say, with z axis. What about phi? Phi is the angle made by the projection vector on, what is this plane? This is xy plane, on xy plane with the x axis. So, we have defined these three variables x, y and z. Now, you can see this r can vary from 0 to infinity. It is measuring from this. So, it can vary indefinitely along this direction. So, the limit of r can go from 0 to infinity. What about theta? Theta can go from, let's say, from along this z axis, theta equals to 0. So, it can vary from 0 to pi. What about phi? Phi, you can see it can show you a round. Okay. So, this is 2 pi in this way. So, phi can vary from 0 to 2 pi. Now, to understand them more efficiently, we need to connect these things with the Cartesian coordinate. So, there exists some relationships with the Cartesian coordinate. Let us say x is equals to r sin theta cos phi, y is equals to r sin theta sin phi, and z is equals to r cos theta. Now, the question is, how do they come? Okay, first of all, let us talk about z is equals to r cos theta. You see, this is r. Okay. Now, let us join this. So, the component along this will be r cos theta. This is pretty straightforward. This is your r cos theta. Okay. Now, this projection, you can imagine it in this way. Okay. So this whole thing is r cos theta. So z is equals to r cos theta is understood. And what about this component? This will be r sin theta. So this thing is falling here. So this is r sin theta. R sin theta is making an angle phi with x axis. So what will be this component? Okay, let's draw this one also. If this is r sin theta, this will be your r sin theta cos phi, and you know, if we consider this point to be x y g, so you know this is x, this is y, and this is z, and that is why we get r x is equals to r sin theta cos phi. And if this is r sin theta cos phi, if this is r sin theta, what will be this component? This component will be r sin theta sin phi. That is why we get r sin theta sin phi, and z is equal to r cos theta. This is quite straightforward. Okay, so once these three things are done, what about r? R is equals to, you see, root over x square plus y square plus z square. R is defined. We need to find out theta. What is theta? If you take the ratio from this third relation, you can find out theta. What is theta? Theta is equals to cos inverse z by r. So two variables is are obtained. What is left? Phi is left. How can you find out phi? If you take the ratio x by y or y by x, you will take, then you will get tan phi. So from this we can get phi is equals to tan inverse y by x. So in this way we have defined the three variables r, theta and phi. Now unit vector along r is r cap, unit vector along theta is theta cap, and unit vector along phi is phi cap. What about their direction? So direction of r is very easy to understand. It will be along this direction. This is your r cap direction. And you see theta will be perpendicular to r cap direction, and you can see this is the direction of theta. So the theta direction will be along this direction. Okay. This is your theta cap, and phi cap direction you can see along this phi is changing. So phi cap direction will also be like this. This is your phi cap direction. R, theta, phi, they will be perpendicular. You see, r cap cross theta cap should give you phi cap. You can consider it in this way: r cap, theta cap, phi cap. They are perpendicular to each other. If you take the cross product of r and theta, you get phi cap. If you take the cross product of theta and phi, you get r cap. If you take the cross product of phi and r cap, you get theta cap. And if you reverse the order, you will get a negative sign. Okay. Now, as it was very straightforward in case of Cartesian coordinates, the length element, this is not so straightforward in spherical polar coordinate. So the length element in spherical polar coordinate we will talk about. Length element is very important. From length element we can get the idea of surface element and volume element. So In spherical polar coordinate, length element is given by dl is equals to dr r cap plus r d theta theta cap. You see, along r change is dr, along theta cap change is not simply d theta, it is r d theta, and along phi cap change is not only d phi, it is r sin theta d phi. So, this you need to understand. So, let me just show you how you understand these things. Okay. So, first of all, let us say we defined the vector r. Okay. You have defined vector r like this. Now, any change in r is dr. So, dr will be like this. This is your dr. Okay, this dr is happening along r cap direction. So, this is pretty straightforward. Now, what about this r d theta, change along theta? So, you see, when you change theta, it is showing change along this. Okay, let me just show you this. Okay. So, let us say this is your r and you have given a d theta amount of displacement. So, obviously, this will again be r. Your change is being carried out along this direction. So, this is r, this is r, this is r d theta. Angle is equal to arc by radius. So, that is why we get an change in theta is r d theta. This is the second one. Now, how do you apprehend this? Change in phi is r sin theta d phi. So, what is happening actually? So, let us say this is the scenario, this is r, okay, and let us say this is z axis. So, it is making an angle theta with this. Now, as I have already told you that what is phi? To get phi, we have to take the projection on the xy plane, right. So, let us say this is the projection. So, what will be this thing? This will be your r sin theta. Now, when you are changing phi, what you are doing? You are rotating this. So, r sin theta is remaining fixed, only change is happening along, you see, change is happening along this, but r sin theta will remain same, na? Right. So, previously let us say r sin theta along this, now you are giving some change and r sin theta you are giving some change in r sin theta. So, this is also r sin theta. So, you are giving change in angle d phi. Okay. So, you just add this. So, we are drawing this thing above here. So, this is what, using the same logic, r sin theta, this is also r sin theta, right, because you are considering on the same plane, xy plane. So, this is nothing but r sin theta d phi. So, this is the direction of change of phi, which is r sin theta d phi. So, I hope you have understood the change in different direction. This is along r direction, this is along theta direction, and this is along phi direction. Okay. This is the length element, and volume element, this is very small thing. So, let us do volume element, then we will go for the area element. For volume element, what do you do? Volume element is a scalar, you know. D tau. So, what you do? You just multiply these things, dr, r d theta, r sin theta, d phi. So dr multiplied by r d theta multiplied by r sin theta d phi. So what do you get? You get r square dr sin theta d theta d phi. That is why we write the volume element as r square dr sin theta d theta d phi. Okay, so I hope this is understood. Let's go to the area element now. When we will talk about area element, we will first talk about the closed surface. Okay, closed surface. In a spherical polar coordinate only we deal with only closed surface. So open surface will not come into picture. So let's take the usual example of a sphere. Okay, this is not a circle, this is sphere. Let's say sphere which has radius, let's say r. If you want to define a surface element on the surface of the sphere, how do you define it? Obviously the direction will be along r-CAB direction. This is pretty straightforward. So remember one thing, the direction will be along the variable which remains unchanged. If you consider this surface of the sphere, what is unchanged? Radius, r variable is unchanged. Whatever point you consider on the surface, r is not changing, radius of the surface is not changing. So direction is r-CAB. So direction of surface will be along the variable which remains constant or not changed. So if I call this area to be dA, how do you write dA? dA we write, remember this thing, here what is not changing? R is fixed. So this dr will be 0 and other thing will multiply r d theta r sin theta d phi. What is r here? R is capital R here. Okay, na? Here your r, it can vary for this whole sphere. If you consider, the limit is not 0 to infinity, it is 0 to capital R. For theta it can vary from 0 to pi, for phi it can vary from 0 to 2 pi. So dr is 0, so r d theta into r sin theta d phi. So small r is capital R here, so r d theta into r sin theta d phi, and the direction is r-CAB, and that is why we write r square sin theta d theta d phi r-CAB. And we know that the total surface area of a sphere, what is the total surface area? We know it, 4 pi r square for a radius r. So we can evaluate, this is the infinitesimal area. If you consider the total area, let's say total area, how should you get? Total area, let's say S, total area S will be, if you consider like dA over the whole sphere, okay, whole sphere if you consider, so r is constant, so r square is outside, integration sin theta d theta d phi. So theta is varying from 0 to pi, pi is varying from 0 to 2 pi. So r square, this value is 2, this value is 2 pi, and that's why we write the surface area of a sphere is 4 pi r square. Okay. This is a case of a full sphere. How do we tackle the element if you are given a hemisphere? Let us take the case of a hemisphere. Let us draw a hemisphere first. So, it is not looking good. So, this is a hemisphere, let us say, and it has the same radius r. Now, can you tell me in this hemisphere how the variable change? R variable as usual, it can vary from 0 to r. For theta, how it can vary? You see, it's a half sphere, so theta will go from 0 to pi by 2, not pi. But for phi, there is no restriction, so it will be as usual 0 to 2 pi, right? Now, let me ask you a question. If you want to define an area element on this surface, how will you define the area? It is pretty straightforward, that you can understand the direction of area is r cap. There is no doubt in that. So, I am calling this area A. So, this is dA. So, what will be the area? What is fixed here? If you consider this curved area, radius is same. Either you consider this surface area here, or you consider the infinitesimal surface area here, or here, or here. At each and every place, radius is same, small r is fixed. So, dr will be 0, r is fixed, means dr is equals to 0. Now, go to the area element. So, dr is not contributing because our change in r is 0, r d theta into r sin theta d phi. But on the surface, curved surface, what is this capital R? Capital R is, very small r is capital R. So, you will write r d theta times r sin theta d phi, right? And what is unchanged here? The variable r is unchanged, so the direction will be r. So, you can also write it as a note. Direction of area will be along the variable which does not change. So, that is why we write this infinitesimal area to be r square sin theta d theta d phi r cap. Now, if I ask you like what will be the area along here on this surface. So, as usual, you know the direction will be always outward drawn normal. So, the direction will be along this. What is this direction? Okay. So, let us call it dA1 and this is this 2. What will be this dA2? If you consider this plane, what is fixed? R is fixed? No. I am drawing this image outside here. Look, I am drawing only the base outside. This is the thing, okay? Just, and we are considering, let us say, this amount of area. This is the direction. Here, you see, if you consider an element here, r will be something. If you consider an element here, r will be something. So, r is not fixed here, r is variable here. But here you see, what is fixed? Theta is fixed. At each and every point, what is theta? Theta is pi by 2. So, change in theta will be 0. So, can you tell me what will be dA2? Let us move. dr is changing, so dr will sustain. D theta, theta is fixed, so this second term will not come. So dr r sin theta d phi, okay, dr r sin theta d phi, dr r sin theta d phi, and as I told you, whatever variable will be fixed. So here theta is fixed, so the direction will be theta cap. Now let's do this. Theta is pi by 2, so we can put the value of theta to be pi by 2 here. Okay, sin pi by 2 is 1. Okay, here it is r dn. So r square dr d phi theta cap. Okay. अच्छा, यहाँ पे एक ही आर है ना, ठीक है, एक बार चेक कर लो गाइस, आर डी आर डी एफ आई थीटा कैप. So I hope you have understood. Now one example of this volume element we can take up. Let's say I am giving a question. Find the volume of a sphere of radius r. So you know already the expression 4/3 pi r cube. So using spherical polar coordinate, how can you evaluate? Any infinitesimal volume element, if you integrate over the whole volume, you should get the total volume, right? Total volume V. We know the volume element expression is r square dr sin theta d theta d phi. So if you consider a sphere, then you can see there r varies from 0 to, let's say, capital R. If you consider the radius to be capital R, theta 0 to pi, phi 0 to 2 pi, and that is why we get, here it is r cube by 3, here it is 2, here it is 2 pi. So that is why we get 4/3 pi r cube. In a very simple straightforward way we can deal with things. So I hope you have understood the surface element in spherical polar coordinate. Let's now talk about the expressions of gradient divergence curl in this coordinate system. Gradient divergence curl and Laplacian in spherical polar coordinate. First of all, let's take a gradient. How the expression change? Gradient of a scalar. So del f upon del r cap plus 1 by r del f upon del theta cap plus 1 by r sin theta del f upon del phi cap. Divergence. Look, this formula will be very useful while you will study electromagnetic theory. divergence of, let us say, vector A, 1 by r square del del r square AR plus 1 by r sin theta del del theta sin theta a theta. This AR, a theta, a phi, these are the components of vector A in the spherical polar coordinate, plus 1 by r sin theta del a phi by del phi. This curl expression is little bit hard to remember, but we have to remember curl of A. This is 1 upon r square sin theta. First we write the unit vector r cap. Here not simply theta cap, it is r theta cap. Here it is not simply phi cap, it is r sin theta phi cap. Del del r, del del theta, del del phi. Here we write AR, here we have r a theta, here you have r sin theta a phi. So gradient, divergence, curl, and finally Laplacian. These four things we will do in all the coordinate system. So Laplacian is denoted by grad square f. So grad square is the Laplacian, f is a function. 1 by r square del del r square del f by del r plus 1 by r square sin theta del del theta sin theta del f by del theta plus 1 by r square sin square theta del square f by del phi square. So these are the expressions of gradient, divergence, curl, and Laplacian in spherical polar coordinate. Just note it down. So from up to this part, the things are pretty trivial. Now we have to connect this spherical polar coordinate with the Cartesian coordinate. So our next topic is how to transform the Cartesian coordinates to spherical polar coordinates or vice versa. So you can give the heading, how to convert how to transform Cartesian coordinates to spherical polar coordinate. This is very important, guys. Questions may come from this. These are basically a fundamental concept which you must learn to solve questions of electromagnetic theory. So what we have our vector in Cartesian coordinates, let's say ax, x cap, ay, y cap, az, z cap. This is in Cartesian coordinate. Now we wish to convert it to a vector in spherical polar. In spherical polar, ar, r cap, a theta, theta cap, a phi, phi cap. This is in spherical polar coordinate. But how we can do this? That is the question. You know, when we calculate ax, what you do? Let's say this is a vector A, this is x cap direction. So to get ax, what you do? Ax is nothing but component of A along x cap direction, means we take the dot product, right? So this is a pretty much basic concept we have. So in a similar manner, if I want to calculate AR, what is AR? AR is like the component of A along r cap direction. So A dot r cap. What is A theta? A theta is like component of A along theta cap direction. So we have to take the dot product. A phi is nothing but the component of A along the phi cap direction. So what you can write? A is this Ax x cap and all. So we can write it as Ax x cap dot r cap. So it is like we have taken the dot product with r cap of this vector. Okay, Ay y cap dot r cap, Az z cap dot r cap. Here also Ax, we have taken the dot product of A with theta cap. So x cap dot theta cap, Ay y cap dot theta cap, Az z cap dot theta cap. Similarly, it is x cap dot phi cap, Ay y cap dot phi cap, Az z cap dot phi cap. Now the problem is we do not know how to evaluate this thing x cap dot r cap. This thing we do not know. This thing we do not know. This thing we do not know. So for that we are doing a very interesting thing. So let's make a table. A table like this. Our main target is to evaluate these terms. X cap, y cap, z cap we are writing, here we are writing r cap, theta cap, phi cap. First of all, let's write the expressions which we know. X is equals to r sin theta cos phi, y is equals to r sin theta sin phi, z is equals to r cos theta. So whenever you want to calculate the dot product x cap dot r cap, what will be this? It is like taking the derivative of x with respect to r. So this will give you sin theta cos phi. Y cap dot r cap. So similarly derivative of y with respect to r. So this is sin theta sin phi. Similarly this z cap dot r cap is cos theta. When you consider x cap dot theta cap, so r derivative we have already taken, so r you have to omit. So derivative of this sin theta cos phi with respect to theta. So this is cos theta cos phi. This is cos theta sin phi, and derivative of cos theta is minus sin theta. Once you have considered r and theta, you have to focus only on phi. So x cap dot phi cap means derivative of cos phi, that is minus sin phi. Y cap dot phi cap, so derivative of phi cos phi, there is nothing left, so this will be 0. So let me just tell you once again what we are doing. So whenever you want to calculate x cap dot r cap, you have to take derivative with respect of x with respect to r. Okay, once r is done, you will go for x cap dot theta cap. You have to take derivative of this remaining thing with respect to theta. Once you are done with theta, we will go for phi. So we will take the derivative of the remaining thing with respect to phi, and you get this one. Now you are in a position to tell what is the value of x cap dot r cap. This will be this. This will be your x cap dot r cap. Let's say z cap dot theta cap. Z cap dot theta cap means it will be minus sin theta. Let's say you want to know x cap dot phi cap. X cap dot phi cap is this minus sin phi. So in this way you can find out this. Now the question is, can you express these unit vectors along the Cartesian in terms of the Cartesian unit vectors? What I want to mean, can you express, let's say, r cap, theta cap and phi cap in terms of x cap, y cap, z cap? Yes, we can write. So r cap is nothing but sin theta cos phi x cap plus sin theta sin phi y cap plus cos theta z cap. Okay, just copying this thing. Okay, so we are now in a position to write r cap. What will be r cap? It will be sin theta cos phi x cap plus sin theta sin phi y cap plus cos theta z cap. Similarly, if you want to write theta cap, it will be cos theta cos phi x cap cos theta sin phi y cap cos phi. We have written it incorrectly, the minus sign will come. Cos theta cos phi, cos theta sin phi and minus sin theta, minus sin theta z cap. And phi cap is simple, minus sin phi x cap plus cos phi y cap. There is no z component. So in this way we can write the unit vectors in a spherical polar coordinate in terms of the unit vectors in Cartesian coordinate. Okay, let's take a problem like where you can utilize this. Okay, look at this problem. In a spherical polar coordinate r theta phi, the unit vector theta cap at this point. So this is pretty straightforward. In a spherical polar coordinate, we talk in terms of r, theta and phi. Obviously the value of r is 10, value of theta is pi by 4, value of phi is pi by 2. You have to find out theta cap. So if you do not know this technique, you will not be able to do. But if you know that the value of theta cap, we have just written, value of theta cap is cos theta cos phi I cap plus cos theta sin phi j cap minus sin theta k cap. Now the value of theta cap at this point 10 pi by 4 pi by 2 will be, so you have to put theta is equals to pi by 4 and phi is equals to pi by 2 and r is equals to 10. So r is not useful here. So cos pi by 4 cos pi by 2 I cap plus cos pi by 4 sin pi by 2 j cap minus sin pi by 4 k cap. So cos pi by 2 is 0, cos pi by 4 1 by root 2, sin pi by 2 is 1. So 1 by root 2 j cap, sin pi by 4 is 1 by root 2, so minus k cap. So 1 by root 2 j cap minus k cap. So that is given in the option D. So in this way we can easily handle this kind of problems. Good evening, Neha Prasik. So, two coordinate system we have completed, Cartesian and spherical polar. Let us go for the cylindrical polar coordinate. After that, we will go for plane polar. In one lecture, we will be covering all the coordinate systems. Cylindrical polar coordinate system. So, if you have understood the spherical polar, cylindrical polar is very easy and it will follow the previous discussion. So, here three things will be there. Look, in Cartesian we have x, y, z. In spherical polar we have r, theta, phi. In cylindrical polar we have r, phi and z. Sometimes people use rho, phi, z also. This z is same of the Cartesian coordinate. Whatever thing z represent in Cartesian, it represents same thing in cylindrical polar. So, that is the similarity it has. Okay. So, for this also what we have to do? We have to take up the coordinate first. कंटिन्यू क्लासेस नहीं होती है आपकी, हाँ अभी से शुरू कर रहे हैं हम लोग, कंटिन्यू क्लासेस अभी करेंगे, ठीक है. सो दिस इज योर एक्स कैप, वाई कैप, जेड कैप. So, if you want to define any point in the cylindrical polar coordinate, say point P, how do you define? You know about the x, y, z thing. Okay. So, if you had to define this point in Cartesian coordinate, what you would have done? You will go x distance along x axis, you would go y distance along y axis and z distance along z axis. So, this would be your x, this would be your y, this would be your z. What about in cylindrical polar coordinate? So, we have to define for r. One difference with spherical polar coordinate, in spherical polar coordinate r is measured from the origin, but in cylindrical polar coordinate r is measured from the z axis. This is the one very fundamental difference. Okay, this will be r, this is not r, not from the origin but from the z axis. Okay, r here, r is the distance from the z axis, not from the origin, and consequently the direction of r will be perpendicular to z axis. So, this will be the direction of r, this is your r cap. Now, what will be the phi thing? To get phi, we have to take the projection on the xy plane. Okay. So, projection of r is on the xy plane like this. So, this is r, this will again be r, this is the projection. Whatever the projection making angle with x axis, that will be your phi. So, this is your phi. So, phi is the angle made by the radius vector or r. Okay, let us write it, made by the projection of r on the xy plane with x axis, and z is z, whatever z you have in your Cartesian coordinate, same z will be there. So, what will be the direction of phi? As you can see, phi is changing along this direction. So, phi, direction of phi will be along this direction, simple. So, this is the phi cap direction, and z cap direction, you say this is the direction of z cap in spherical Cartesian coordinate. So direction of z cap will be like this. Remember one thing, that these unit vectors are perpendicular to each other. In case of spherical polar coordinate also you have seen r cap, theta cap, phi cap, they are perpendicular to each other. X cap, y cap, z cap, they are perpendicular to each other. Here also r cap, phi cap, z cap are perpendicular to each other. Okay. Now we know three relations here. If this is r, what will be this thing? This projection r is making angle phi with x axis, so this will be your r cos phi, and consequently this distance will be r sin phi. That is why in cylindrical polar coordinate we write x is equals to r cos phi and y is equals to r sin phi, and z is z. There is nothing special about z, so z is z. तमाल क्या बोल रहा हो? गुड इवनिंग, काइंडली मेक अ वीडियो ऑन पोस्ट जेस्ट अपॉर्चुनिटीज रैंक वाइज. या विल ट्राई. Nice suggestion. So we are interested in these three coordinates r, phi and z. What is r here? We have to relate r with the Cartesian coordinates. R from this you can easily see it is nothing but root over x square plus y square. R is defined. Now phi. How can you define phi? You can take the ratio. Phi is equals to r sin phi by r cos phi, so tan phi, so phi is equals to tan inverse y by x, and z is z. So you understood? Now we have to define the line element, surface element and volume element in this coordinate system. And before that, let me give you another idea, like the range of these three variables. What is the range of r? Range of r is as usual, it can go from 0 to infinity. Phi, as usual, you can see that it is ranging from 0 to 2 pi, and z, you see this is origin. Z can vary from 0 to infinity, and in the negative side also it can vary 0 to minus infinity. So this is minus infinity to plus infinity. It has a wider range. Okay. So let's write the line element in cylindrical polar coordinate. So you can give the heading line element in cylindrical polar coordinate. Now when you take a line element, you see you have to consider the change in r coordinate, change in phi coordinate, change in z. Change in r is very straightforward. If this is one point, if you change little bit, it will be along this direction. Change in z is also straightforward along this. But what about the change in phi? So change in r and z is trivial, so we are considering change in phi. So if you change phi, you see an angle is made. Okay. So let's say we have this r and we are making a small change in phi. This is r, this is also r. We are making some change in phi, so d phi change. So change will be like this. This will be the change in phi cap direction. What is this? This is r, this is d phi, this is r d phi. This much is the change in phi. Change in phi is not simply d phi, it is r d phi. Okay. So let's write the line element. To write the line element dl, change in r is dr, no issue, r cap. Change in phi we have just evaluated r d phi along phi cap direction, and change in z is dz along z cap direction. So if you understand this simple thing, then it will be very easy for you to understand complex things. Book wise है या topic wise? Book wise अभी we are dealing with mathematical physics. Okay. So this is a line element. I hope you have understood line element. Volume element is pretty straightforward. So let's first consider volume element. How to define volume element? Volume element means the product of this thing. So you see dr, r d phi, dz. And that is why we write the infinitesimal volume element in cylindrical polar coordinate to be r dr d phi dz. Volume element is a scalar, so there is no issue of direction. Now the main headache is the surface element. So how to deal with surface element in cylindrical polar coordinate? Look, needless to say, when we have an object with cylindrical symmetry, we will use cylindrical polar coordinate. We have spherical symmetry, then for those objects we will use spherical coordinate. Like if you have a football, a sphere, then you will use spherical polar coordinate. If you have a cylinder, a pen like this, so for this kind of cases we will consider cylindrical polar coordinate. So obviously for this case we will be considering the cylindrical polar coordinate. So I am giving you a scenario. First of all, let us take a cylinder. सिलेंडर पे लाइन कहाँ से आ गया? Okay, let's make a cylinder. Okay, let's now fix the coordinate system in this cylinder. It is situated, the origin is situated at the middle of the cylinder. Okay, so this is your x cap direction, this is y cap direction, this is your z cap direction, and center of the cylinder is the center, our origin. Okay. Length of the cylinder is, let's say, L. So if you consider this surface, what is this surface called? This surface is z is equals to, let's say, L by 2 surface. Okay, this much is L by 2 and this much is another L by 2, so total is L. What about this surface? This surface is z is equals to minus L by 2. Now I am assuming we want to take an element on the upper surface. So what will be the direction? Outward drawn normal. This will be the direction. If you take an element in the lower surface, what will be the direction of area? Outward drawn normal. Okay. So for this cylindrical case, let's write specifically how r can vary. To define this cylinder, how r can vary? R can go from 0 to capital R. If we consider the radius of this cylinder is R, so R will vary between 0 to capital R. What about phi? Phi can vary as usual 0 to 2 pi. What is Z? Z, you can see it is varying from minus L by 2 to plus L by 2. Now we are interested in writing the surface element. Let's say one surface element we are considering here on the curved surface, and as you can see, what will be the direction of this area element? Obviously it will be like this. This will be the direction of the area element. What is this direction? This is nothing but r-cap direction. So, if I want to write this, r is equals to capital R. This is how we define this curved surface. So, if I write the area element, this is your dA. What will be this value? dr along the curved surface, we have the fixed radius, right? So, no change in dr. So, dr will be 0. r d phi. So, here r is equals to capital R. So, r d phi. Here dz is dz, and which is the fixed variable here? R is not changing. So, the direction will be your r. So, this will be your r d phi dz r cap. Understood? Let us say we want to define a surface element on the z is equals to L by 2 plane. Means this, if this is your, let us say, let us name it dA2 and this is dA1. So, this is your dA1. So, any surface element on the z equals to L by 2 plane, let us say this is be dA2. What is fixed here? You see, on the z equals to L by 2 plane, z is fixed. So, obviously, this dz will be 0 and r is not fixed. If you consider an element here, okay, r will be something. If you consider an element here, r will be something, here r will be something, here r will be something. So, change in r is there. So, dr, what about r d phi? Phi is also changing, r d phi. What is fixed here? Z is fixed here. So, direction will be your z cap. So, this is r dr d phi z cap. I think now you have understood how to tackle with surface element in spherical polar coordinate and cylindrical polar coordinate. Chalo. Let us quickly talk about the gradient divergence curl in this coordinate system, which is important. Gradient divergence curl and Laplacian in cylindrical polar coordinate. First of all, gradient. So, you have to remember these things, okay? Because in electromagnetic theory, when we will be given some cylindrical object, you may have to use this, okay? In applying Gauss law and all, the differential form of Gauss law. What about divergence? Divergence is defined for a vector A 1 by r del r. AR is the component along r direction, A phi is the component along phi direction, and AZ is the component along z direction. What about curl here in this coordinate system? So, in spherical polar coordinate we have r 1 by r square sin theta outside, here it is 1 by r, okay, r cap, r phi cap, z cap, del r, del phi. Look, these small details are important. It is not like only phi cap, it is r phi cap. Here it is AR, here it is r a phi. These things you have to remember, otherwise you won't be able to solve problems based on this. Okay, I think in magnetization topic, where you will be calculating, I think, surface current, then this formula will be useful. Lastly, Laplacian grad square Nabla operator 1 by r del del r times del f by del r 1 by r square del square f by del phi square del square f del z square. So, in this way we can write gradient, divergence, curl and Laplacian in cylindrical polar coordinate. Okay. So, once it is done, let us now similarly tackle how to convert Cartesian coordinate to cylindrical polar coordinate. Okay. So, once you have understood the spherical polar coordinate case, it will be very easy for you to understand the cylindrical polar case. So, how to transform Cartesian coordinates to cylindrical polar coordinates. Once we are done with this, we will consider another one plane polar, then we will wrap up the session. Okay, I will be back in 1 or 2 minutes, just hold on. Okay, let us resume. We have a vector A, let us say in Cartesian coordinate. It has 3 component Ax. Let us say previously we have done with x cap, right? So, let us follow the same terminology. Ay, y cap, az, z cap. This is in your Cartesian coordinate, and we want to convert it into cylindrical polar coordinate. So, in cylindrical polar coordinate will be AR r cap, A phi phi cap, AZ z cap. And as I have already told you, what is AR? AR is nothing but the component of A along r cap direction. Similarly, A phi component of A along phi cap direction. AZ is nothing but the component of A along z cap direction. So, taking the dot product of A with r cap means Ax x cap dot r cap plus Ay y cap dot r cap Az z cap dot r cap. Similarly, write this Ax, okay, x cap dot phi cap Ay y cap dot phi cap Az z cap dot phi cap, and this one finally x cap dot z cap Ay y cap dot z cap Az, okay, z cap dot z cap. Look, z cap is creating no problem, but what about this x dot r cap, x cap dot phi cap? How to calculate this? So, to do that in a similar manner, we are constructing a table. Okay, 3 more lines. This is your x cap, y cap, z cap, r cap, phi cap, z cap. So, we will be considering the similar terminology here. X is equals to r cos phi, y is equals to r sin phi, and z is equals to z. So, to calculate x cap dot r cap, you have to take derivative with respect to r. So, what is remaining? Cos phi. Y cap dot r cap, sin phi. Z cap dot r cap, there is no related r related term, so this is 0. Once you are done with r, we will go for phi. So, we will forget r. So, x is like cos phi. So, derivative with respect to phi is minus sin phi. Derivative with respect to phi is cos phi. Derivative with respect to phi is nothing, 0. For x and z, nothing is there in nothing of z is there in x. So, this is 0. Similar for y, 0, and z with respect to z. So, this is 1. Okay. So, in this way you can write, and in the like we have done in the previous case, here also we can write these unit vectors like r cap, phi cap, z cap in terms of the unit vector of the Cartesian coordinates. So, r cap, you can now tell me cos phi x cap plus sin phi y cap. Phi cap will be minus sin phi x cap plus cos phi y cap, and z cap is z cap. Okay, we can write it in this way. One problem I think came in JEST based on this. Let's do it. Okay, where is the problem? Okay, look at this problem. The vector field xz I cap plus yj cap in cylindrical polar coordinates. So, you are given a vector in Cartesian coordinate, you have to convert it into cylindrical polar coordinate. E rho cap, E phi cap are the unit vectors along rho cap direction and phi cap. Rho is r here. Okay. E rho cap is nothing but r cap. E phi cap is nothing but your phi cap, and E z cap is nothing but your z cap. So, you are now in a position to solve these problems very simply. Simply you can do this problem. So, you are given A, which is x z I cap plus y j cap, and you have to find out the same thing in cylindrical polar coordinate. So, what is Ax here? Ax is nothing but xz. What is Ay here? Ay is nothing but y, and Az is 0, right? First of all, we need to write this. So, E rho cap, okay, let us first write what will be the form in cylindrical polar coordinate. If you follow the same terminology which is given in the question, so it is like A rho cap, okay, let us write it E rho cap, then A phi, E phi cap, Az, Ez cap. Okay. So, we need to calculate A rho. What is A rho? A rho is nothing but the component of A along rho direction, right? So, this is nothing but Ax x cap dot E rho cap plus Ay y cap dot E rho cap Az z cap dot E rho cap, right? Now, you can put the values. What is Ax? Ax is equals to x into z. Okay. So, x we have to put in cylindrical polar coordinate. ओके, इसमें यहाँ पे थोड़ा सा हम लोग कर सकते हैं, x इंटू जेड इज इक्वल्स टू रो cos phi times z and y is equals to rho sin phi and z is equals to this. Okay, so ax is equals to rho cos phi into z x into z and x cap dot e rho cap. What is this? Okay, हम लोग एक काम करते हैं, let's copy this thing. This will be useful for us. Paste. Okay, so what we require? We require x cap dot e rho cap. So x cap dot r cap, so that is cos phi. So we are putting cos phi. Ay is rho sin phi. Y cap dot e rho cap means this sin phi, right? And as it is not there, so we don't bother about that. This is rho cos square phi into z plus rho sin square phi. Okay, so a rho is found out. Let's calculate a phi. A phi is a component of a along the phi cap direction. So this is ax x cap dot e phi cap, ay y cap dot e phi cap, az z cap dot e phi cap. So similarly x is rho cos phi times z x cap dot e phi cap. So this is minus sin phi, right? Minus sin phi. Ay rho sin phi and y cap dot e phi cap is cos phi. And az is 0, that is making our calculation easy. So this is nothing but rho cos phi sin phi if I take common, so 1 minus z. So your a becomes rho cos square phi into z. So you can take rho common, na? Sin square phi. This is the component along rho cap direction, and for phi rho cos phi sin phi 1 minus z e phi cap, and there is no z component, and it is matching with option D, I think. D, or which option it is matching? Z cos square phi plus sin square phi. Rho sin phi cos 1 minus z. ऑप्शन ए के साथ मैच करो ना, रो z cos square phi plus sin square phi, rho sin phi cos phi 1 minus z. Yes, option 1. Anyways, so we have covered all those three coordinate system: Cartesian, spherical polar and cylindrical polar. One small coordinate system is left, that we will also cover. Okay, okay, that is plane polar coordinates. Plane polar coordinates. Look, in Cartesian x, y, z, spherical polar r, theta, phi, cylindrical polar rho phi z or r phi z. In plane polar coordinate we have two coordinates, r and theta. Okay, So, it will be easier for us if we go with our known coordinate system x, y, Cartesian. This is 2-dimensional Cartesian coordinates x cap, y cap. Know this thing, this plane polar coordinate is valid for 2-dimensional cases. Okay. So, if you want to define any point, you know, you will go along x direction, then you will go along y direction. What about this plane polar coordinate? What is r here? So, r again here it is measured from the origin. This is your r, and you know this angle is 90 degree between x cap and y cap. So, if you want to give the direction of r cap, it is like this. This is the direction of r cap. Remember one thing, that theta cap is perpendicular to the r cap direction. So, your theta cap will be along this. This is your theta cap, and this angle will be 90 degree. So, 2D Cartesian is dealt with two coordinates x and y, and plane polar we have r theta. How they are related? X is equals to r cos theta, y is equals to r sin theta. Straightforward. Okay, let us do one thing. We are drawing this same thing in a single picture. Okay. So, we had our x and y. This is x, this is y. Let us not change them. Okay, this is your x cap direction, this is your y cap direction, and you see we can take this thing at the origin. Okay. So, this was your r. Okay. So, I am trying to do something. Let us draw a semicircle like this. Obviously, this will also be r, and theta is perpendicular to this. So, this will be theta. This is your r cap, this will be your theta cap. And as you know, the angle made by r cap with x axis, this angle is theta. Okay, this theta is this angle made by the radius vector with x axis, and the angle between theta and r, you know, this is pi by 2, right? So, what is the angle? What is this angle? This angle will be theta plus pi by 2. So, theta cap direction is making an angle theta plus pi by 2 with x axis. Okay. So, when we want to write, let us say r cap, how do we write? R cap in terms of x cap and y cap. You can see r cap is making an angle theta with x axis. So, it is cos theta x cap plus r cap is making 90 degree minus theta angle with y cap. So, this is sin theta y cap. So, in this way we have written the unit vector along r direction in terms of x cap and y cap. How will you write the unit vector along theta cap direction? So, theta cap, you can see it making an angle theta plus pi by 2 with x axis. So, instead of cos theta, it will be cos theta plus pi by 2 x cap and sin theta plus pi by 2 y cap. Theta plus pi by 2 means this is in the second quadrant. In second quadrant, cos has negative value. So, this is minus sin theta x cap, and in second quadrant sin has positive value. So, this is cos theta y cap. So, in this way we can write the unit vectors of plane polar coordinates in terms of the unit vector of Cartesian coordinates. Okay. Okay. Now, let us take an example so that you understand it better. One example I am giving you. Chalo. And after this we will wrap up the session. I am giving you one vector in let us say plane polar coordinate 7 E r cap. E r cap is the unit vector along r cap direction minus 3 E theta cap. So, your E r and E theta cap, these are the unit vectors in plane polar coordinate, let us say. So, what is Ax? Ax, we know the component of A along x cap direction, isn't it? So, 7 E r cap minus 3 E, अच्छा हम लोग थीटा लिया फाई लिया थीटा, ठीक है, थीटा कैप डॉट एक्स कैप. So 7 ER dot ER cap dot x cap means r cap dot x cap. Okay, r cap you see cos theta x cap plus sin theta y cap. So we are taking with dot product with x cap. So this will give you cos theta, right? So this is 7 cos theta, and r cap means y cap dot x cap, that will be 0. So no term is coming, minus this 3 E theta dot x cap means theta cap dot x cap. So this will come minus sin theta, right? So minus sin theta. This is equals to 7 cos theta plus 3 sin theta. Let's say we want to calculate AY. So component of A along y cap direction, as usual 7 E r cap minus 3 E theta cap dot y cap. So what will come here? E r cap means this sin theta, we are taking dot product with y cap, so sin theta will come now. So 7 sin theta minus 3 E theta dot y cap, so we have the component cos theta. Okay. So if we give you the value of theta, if theta is given, then we can easily find out Ax and Ay. Okay. So long class. So we have today considered 4 coordinate system. Firstly, we have talked about Cartesian, then we went to spherical polar, after that cylindrical polar and the plane polar. So I think after attending this class, your fundamental will be crystal clear, and whatever question you get in your examination, you will be able to handle. So this was a very important lecture. So long lecture, but we have covered everything. So before I end this session, let me tell you guys, you can get such important 100 topics in a single course on this course, top 100 most important topics for CSIR-NET 2024. This course has been launched. We will be covering 100 total most important topics for the upcoming CSIR-NET exam. This will be valid for 3 months 10 days, means total 100 days. Okay, whenever you will purchase this, you will be using the benefits for the next 100 days, means 3 months 10 days. And ISRO date, exam date has already been announced. You can also go for the test series. Okay, all the links are given in the description. With this note, let's end this session here. I hope you have understood everything, and if you have any question query, you can let me know in the comment section later on also. Okay, so thank you very much. If you are new to this channel, please subscribe the channel and don't forget to press the bell icon. Good night, see you in the next session. Bye bye, take care.